So, welcome everybody to today's afternoon session, and it's my immense pleasure to introduce our next speaker. In the beginning of the week, many of you discussed about potential platforms of quantum computing, and many of you were suggesting ion traps. So basically, now is your time, and Ferdinand Schmidt-Kaler is an extreme expert on the topic, and you should be looking forward to his talk. Let me briefly introduce his CV. Let's see how much I can get it straight away from my memory. So you did your diploma at the TU of Munich with Rempe and Walter, I think, on Swiss single atom maser. And then you did the greatest leap you can do within Munich by changing from TU Munich to LMU for the PhD, which is like the largest leap you can do. Afterwards, you did some postdoc in some labs of slightly non-experimentalists. You might have known the name at LKB, Serge Haroche, and so on. Yeah, you might have known the name. Before then, going to Innsbruck for another postdoc and working with Rainer Blatt. And doing your habilitation there as well. Afterwards, you became full professor at the University of Ulm before finally settling down in Mainz and doing extremely great physics on ion traps. I think this is more or less your scientific CV. The full science will come now, and we are very much looking forward to your talk.
Well, thank you very much. Yeah, that's very kind. So, yeah, I will talk about trapped ions and how to build quantum computers, but this is a long afternoon actually. So I have a lot of topics here, and I want to give you an overview on quantum computing, my personal understanding of what is the field and what is good for. That will be the beginning, that will be kind of an introduction, and then I start even with history, because I'm so old, I'm allowed to talk about history. And then it's going to be really different topics of trapped ions such that you can really understand the system and eventually maybe use it, okay? Because there's open access quantum computers, not only from IBM, they are well known, but also from trapped ions. And we are going for this also. So my intro is structured for this. I say what a quantum computer is not good for. And that's the start, okay? And what it could be good for, I'm really modest. I want to be modest. I don't want to give out here the quantum computer will save the world and so on. But we are going ahead, and this here, what you see here is a small chip, and I've got this chip. I will show it around later for you so you can take it in your hand. It's this small thing. It's the core of the ion trap quantum computer. And in the middle of the slit, there are the ions which are storing the information. So let's start. So that's what I saw just a couple of days ago. Sorry, this is German, but it was a German newspaper. And this was the publicity of some company, Electron. And I just translated here for you. The quantum computer is much faster than the classical computer. For example, you can calculate the climate, you can predict storms or when it doesn't rain. You are much more reliable than the other calculations nowadays. Also, you can help for developing vaccines, and you can do this in seconds, while so far it's done in many hours. Okay. And also later on, this, what we doing with a quantum computer, is more important than printing books according to Gutenberg, more important than the internet, and more important than the development of fire to mankind, okay? So this is by far too much, okay? But he is not scared. Yeah, this is really nonsense. But in this moment, when it comes to Buchdruck and Johannes Gutenberg, I'm really, I'm coming from Mainz. I'm defending this. No, Buchdruck is much more important than quantum computing. I'm still in favor of this. So this is what you typically see in the news, and you get a little bit nervous. So some people sell these machines for millions, and some of them say, okay, I don't have a real quantum computer. What is now really true? So I'm a German professor. I should tell truth. I'm not such a businessman And many of these things are driven by big money, actually. So take it with a lot of warning. So far, there is no quantum computer doing anything reasonable, useful for mankind. That's the status. So that could be the end of the talk, but it's not, because I'm believing that we can change this, okay? That's the point. That's the whole point. This is the roadmap of IBM. Very spectacular roadmap, really a long perspective, starting with small quantum devices, which have only 5, 16, 20 qubits, then 127 qubits, I come to this later. Then here it goes on, there is 200 qubits, 2,000 qubits. Actually, they restructured their roadmap only at the beginning of this year. Before there were a couple of thousands qubits were much earlier, and they had millions of qubits in this time scale. Now they reduced this and they made it more realistic, I think. It's a very good move. But now we are here in this year, I guess, yes, here. So there are now 133 qubits, and even 3 times. So 400 qubits. Is that really true? Can we do quantum computing with 400 qubits? That would be super crazy good. Yeah. Now this is of course not true. Okay, with a quantum device, and I show you an example that features 127 qubits. That's this Kiev device. You can still not entangle 127 qubits. You're far from that. Okay. This is measured by the volume of this quantum computer, and in reality, the record of entangling qubits is a little bit better than 20, okay? So that means in this architecture here, you can talk with this qubit to its neighbors. You see it's a poor connectivity, actually, because if you want to connect qubit number 43 to qubit number 126, you have to swap all this information around here, and when you're doing this with a limited fidelity of gate operations, you end up with only noise. So that's the reality. That's a bloody bad reality with these devices. And still, they publish cool papers, okay? And this was one that was the evidence for the utility of quantum computing. That would be contradicting what I said before. I said, okay, so far nothing has been useful. This is now utility of quantum computing. So that means, okay, they state in this article, actually you find a lot of wrong papers, especially in Nature and Science, but this is, they state, okay, we are now at a level where we are reaching, even in a non-fault-tolerant way, the limits where we can make quantum computers really useful, and nobody can overcome this. Because this is doing a 170 qubit device, it's doing something that nobody can do elsewhere. So then, only 2 days after this was published, some theoretician came out and said, okay, we can exactly simulate the whole thing with our normal computer. No problem, just doing it. It's running much faster, it's running much better also. And then to put it even, to make it really awful, there were some other scientists, they got from eBay an old Commodore 64. That is a really old machine. You have to search the internet to find an old museum, Commodore, and they then made this experiment. They implement the whole circuit on a Commodore 64. And actually they have made it even worse. They have written down the code on a piece of papyrus to show that this can be really casted very simply in a classical setting. So very, very careful if we talk about quantum supremacy or that a quantum computer is outperforming something. We should not do this at the moment, okay? Yeah? Okay, this is the paper, and you can read it, and it's really amazing. You know? So what is the core of a quantum computer? You could think of a quantum computer as a kind of a graphics card for a regular computer for very special purposes. it would help the classical computer to be a bit better. For very special applications, you can use it. And there's, for example, this Mogon. It's a high-performance computer at University Mainz, and we are connecting this with our little small baby quantum computer. And that is only that we have to train this connection, because if you have then a big quantum computer, one day, I show you the way, how to go there, then you have to connect it to a high-performance computer. So we better learn all this software, how to connect it right now. And try some algorithms which are doing this connection, which are using these connections already right now. Of course, at the moment, this is the mighty one. This one is doing much more, and this is just a game. But once the quantum computer is more adult, then maybe it is useful. At the moment, you can connect to any computer, but you know it is not so easy to connect to a high-performance computer, because people have very special programming, very special security measures, and so on. So you better do this in a reasonable way early. So what are the possible applications then? If you have this connection between a quantum coprocessor, I call it, and a high-performance computer. And certainly not the first thing you want to do is breaking RSA. That is certainly not the first thing. I have many reasons, just to mention a couple of them. First of all, it's a super hard problem to do. We need many qubits. We need a really great quantum computer. There are many earlier applications which are much more useful. Second, we are not the evil people, clear. Third, RSA is not any longer useful. So people have found post-quantum encryption schemes which are not mathematically proven to be safe against a quantum computer attack, but I guess they are. So this is, for any reasons, not useful. You may be able then, when this quantum computer exists, say in 5 years, then you may be able to read stored emails which are encrypted, which have been encrypted, but this is then some messages from the past, and maybe you can read the love letter from Prince Charles to Lady Diana or so, if you're interested, and it was encrypted. Maybe you're not so interested in this. So no, you cannot break modern codes. But there are a lot of optimization talks, and especially hard are fermionic problems, and they appear a lot. They appear if you are calculating molecular reactions, because the electrons are the glue in a molecule, and these electrons behave, they are fermions, they behave according to the Pauli principle. They are very hard to calculate on a classical computer, how they sit on the orbitals and how they generate a binding in a molecule. You can also do a simulation of magnetic materials. And then, well, this is now a point, I'm coming to this in detail. What is this noisy intermediate quantum computer, and what is a fault-tolerant quantum computer? A fault-tolerant, error-corrected quantum computer is the ideal machine, and we are far from that. We are doing also baby steps to do this, and I will have a full chapter on quantum error correction. But you can only make quantum error-corrected, or we call them logic qubits, if you take a couple of physical qubits together. So the redundancy of these physical qubits can be used in a clever algorithm, I show you one of them, can be used in a clever algorithm to save the quantum computer a bit against errors. And then it will be, of course, eventually the only way to do this. But if you're taking, for example, 7 physical qubits to make one logic qubit, you need 7 times more. So you have seen people are even not able to entangle more than 20 qubits at the moment, so that would make up 2 logic qubits about, or 3. So then you are starting again from very small numbers of qubits, and your computer is again a baby computer, now a quantum error-corrected baby computer, but still something which is not so helpful. So we are trying, therefore, to bring the noisy intermediate scale quantum computer to a level where you can still hopefully find some applications. And then, at the same time, evolving the quantum correction schemes and making them true. So, of course, I will advertise then our specific Mainz approach. You will learn about the architecture, how we want to scale, and how we want to scale and keep the connectivity of qubits nice and great. Because you have seen in the IBM computer, one qubit is connected to its 2 neighbors, maybe 3 neighbors. In the Google architecture, one qubit is connected always to 4 qubits. There are a lot of these architectures where only very short-range connections are possible. I will show you in the trapped ion setting that you connect one ion qubit to many others. And not only 4, but maybe 10 or maybe 20, okay? And that is, of course, a big asset because this high connectivity makes your quantum computer more, it can execute all algorithms much more efficiently, actually. Yeah, it's obvious because you have not to swap information. And then, at the same time, we have to check out how are these applications. Now, these applications are far from being useful, as I told you, but they are already tested and you have to implement them on a baby computer. You have to test them, you have to optimize them, and that can be only done if you have a 24/7 operation of your devices, that people can access them and really use them and test them and check out what they can do. So that is the menu of my talk. Now it starts. That was just the intro, okay? And I will start with history, then I come to an introduction of how to trap ions, how to cool them. That's the basics. I will then talk you how you encode qubit information into a trapped ion. We know a qubit is alpha 0 plus beta 1, and alpha and beta squared is equal to 1. So you're describing a Bloch vector on a sphere, okay? This is 0, this is 1, this is 0 plus 1, this is minus 1, this is E, this is minus E1, and this is alpha 0 plus beta 1. That's the thing. You need this in a scalable system. You need many of them, and ions are ideal because they are made by nature, by God, and they are all identical. If you don't spoil them, okay? If you don't put a magnetic gradient, or if you don't put some things which are spoiling this, that they are equal. This is a natural qubit system, like atoms, ions. But if you're going to superconducting qubits or quantum dots, you have to grow the structure so perfectly well, or you have to tune every qubit that they are exactly identical. That is a difference. Okay, so you can distinguish between these natural systems and the man-made systems. Yeah, and then I talk about architectures. You have heard already that architecture is really making a big deal if you want to generate a large quantum volume. Otherwise, you cannot connect this qubit with this one. So that is the architecture point. And of course, the architecture comes, well, the architect designs a house, but then somebody has to build it, okay? Then comes to trap fabrication, because this little golden thing which I showed you has to be made. And there are no companies which can just fabricate quantum bit feasible ion traps for you. So you have to make them yourself, and that's what we are doing. And now you have to control them. They have 100 of electric contacts to shuttle these ions around. And eventually they will have maybe 50 different laser beams going in and addressing ions and doing quantum gate operations. And so you need a lot of optical and electronic control. And this electronic and optical control can only be governed. It's so complex if you have good software architecture. And this is separated in a low-level stack, which controls all this hardware, like your driver, which addresses the screen or the hard disk or so, or the USB. And then there's a higher-level architecture, which is your operation system. And then there's an application software on top. Word, Excel, I don't know, yeah? So that's the same for the quantum computer. You have the different stacks of the software and of the compilers. Yeah, we also have to do this ourselves because, well, there's Qiskit, but Qiskit is, of course, optimized for superconducting qubits. It's not exactly doing the hardware control of trapped ions. So this is something you have to develop. And then I will talk to you about this noisy intermediate scale quantum computer versus fault-tolerant quantum error correction. That is this chapter. And then I come to some applications. So that's the menu, and you're really asked to move your hand up if you have some problems, or if you don't understand, or if I'm too fast, or whatever. Or if I'm too slow also, please do it, yeah? Okay, I'm starting with history. That's Wolfgang Paul, and he received the Nobel Prize for inventing the Paul trap. And Theodor Hensch, that was my PhD advisor, he made a lot of funny experiments. So he trapped dust particles by the radio frequency applied to a paperclip. And yeah, you can, that's me and that's Theodor Hensch, long time ago. And yeah, and that is now what you really see in your trap, actually. So I don't know whether this is not a film, yeah. Well, you can then see the ion crystals. So these are now individually observed ions, yeah? So 1, 2, 3, 4, 5, and so on. They are repelling each other because they are singly charged. They have a 1 unit charge, positive. So Coulomb propulsion makes them separated. That is nice because that means you can now tell apart the atoms. If you have neutral atoms, they would be much closer. You have much more problem to say, this is qubit number 17, this is 18. They are so close. In the trapped ions, they have a distance of about 5 micrometer. Yeah? They are not, absolutely, they are not equidistant. I come to this point in detail, but what you can think of, they have Coulomb propulsion with respect to each other. So in the middle, this ion sees the Coulomb propulsion from both partners, from both sides. While this ion is only pushed from one side, and now you can ask, why is it not falling out? That is because it's sitting in a common harmonic potential. So all ions are sitting in this common harmonic potential, but in the inner part, they are pushed from the neighbors from both sides, and that makes the distance in the middle smaller than at the sides. You can also tune the potential to be non-harmonic, and then you can make it more equidistant if you like. But that's the typical situation you have. Yeah. So these ions are allowing us to go to the quantum world. Why is this the case? Yes?
How are they maintained in the same line without using a magnetic field?
There is no magnetic field which is trapping them. That is, I show you the trapping mechanism and explain this in detail. But typically they are sitting along one line, okay? Or you have a trap that's storing only a single ion. That's of course what you don't need for a quantum computer. You want to have something which is in a single line. And then I will go to an extension of the architecture where you have now X and Y junctions such that you can shuttle them across corners and make them much more complex movements. Yeah.
Is there a problem with the very right one?
What a problem?
With the very right one?
Yeah. Why is it so faint? Yes. That is just because the laser beam was illuminating the innermost ions more, because the laser is more stronger at the center in this picture. There is no problem, no. Okay, these ions allow us to enter the quantum world. Why is this the case? Well, you have the trap, and the trap is working in ultra-high vacuums. You need not to keep these ions by anything except an electric oscillating field. And this is an ultra-high vacuum. So it is basically like the Gedankenexperiment of Erwin Schrödinger, where you have a closed box and nobody's looking inside. That is a pretty good approximation to this closed box, because there is no observation, not even in principle. You can have residual gas collisions, possibly, okay? They would be distinguishing between the two qubit state, then you could say this atom collision would tell you apart whether the qubit was up or down, and it measured this qubit. Or you could have some light which projects into one or the other state, but you switch off the light, of course. So there is barely no way to tell the qubit states apart once they are trapped in ultra-high vacuum in this Paul trap. You can also think, well, the next electrode is maybe 200 micrometer away. Could this sense the qubit state? No, it does not, because the qubits are carried and held by the virtue of that charge. But the charge is not the qubit. The qubit is living in the electronic levels of the electron. So that does nothing to do with the trapping purpose. So there is no thing which can tell apart whether this qubit was up or down, 0 or 1. When it's trapped, it's immune against all this. And that means we have super long coherence times. You know, maybe in superconducting qubits, you have this surface, you have built these things, you are doing superconductivity, it's low temperatures, everything is great, but the best coherence times are less than a millisecond typically, maybe 100 microsecond. So you have to be very, very fast in your operations in order not to forget with your quantum computer what you encoded. Now in our case, we have qubits which are living easily a few seconds, and the gate times are in the range of microseconds. So that is a nice separation of time scale. Of course, we have to be better than this, improve even on seconds, and bring it to the minutes and to the hours. But we are deep in this quantum regime with our system. And actually now comes some fun part. This is from the guest book of Rainer Blatt, and I guess you cannot read it, but it was written by the Dalai Lama. It's a long time ago, actually. He came because Anton Zeilinger told him, you can come to Innsbruck and you can see with your naked eye a single atom. And the Dalai Lama is very interested in modern physics, I have to say. He's really a very special person, and I like this very much. And that is the only thing I can really read is this 6 and maybe that is this date, I don't know. But that's the Dalai Lama handwriting. And he was then in the lab. So you see Rainer Blatt in the middle here. Was of course a very, very exciting moment. Everybody was excited. Dalai Lama coming to Innsbruck to see a single trapped ion. And that is the translator. That's his personal, personal monk, his own monk. He translates everything, he does everything. And that is not the monk of Rainer Blatt, but the PhD student of Rainer Blatt, Christoph Raab, yeah? So, and that was a single barium ion. You could see it with your naked eyes, just looking into the viewer. And nowadays, I have to tell you, if you want to be, it became much more democratic. At that time, you had to be really good friends with Rainer Blatt, and then you can watch a single ion. Nowadays, you just have to go to Winterthur in Switzerland, and Jonathan Holm, actually, he built a machine like this. That's exactly looking like the machine which was sitting in Innsbruck. And you look into this here with your eye, you can see a trapped ion. Or you can even see a linear crystal of trapped ions. This I took with my, just with cell phone camera through the objective. Yeah, you see a linear crystal there. It's cool. And barium is a good ion for this because the emission wavelength is in the maximum of the sensitivity of your eye. We are then using in Mainz, unfortunately, we are using calcium. It has a better qubit, we think, but you cannot see UV so efficiently. So that I've never seen a calcium ion. Nobody can see the calcium ion, but barium you can see. Okay, up. These are the ions dancing. You see the. No. Okay, this with sound. Sorry. Okay, so you see them dancing, and that was the Coulomb repulsion, exactly the thing you asked for. Okay, you see them. It's like a spring, and you see the breathing mode. There are different modes of vibration. I will talk about how they come about. You can calculate what these modes are. Okay, now my final history things are coming because of these Nobel Prize winners, Anton Zeilinger, John Klausner and Alain Aspect, they received the Nobel Prize for entangling photons. We know this was typically spontaneous down conversion sources. And these spontaneous down conversion sources, you send in one photon and you get on 2 entangled photon out. But not all the time. Typically you send a photon in and nothing comes out, just this photon comes out, nothing entangled. So it's spontaneous, okay? You cannot trust on this. You cannot say, okay, this I shoot in, this I get out. It's not deterministic, okay? And so they explored the world of quantum entanglement. But before there was this Nobel Prize for Serge Roche and Dave Wineland, and they did control the quantum entanglement by making an interaction by hand, so to say, okay? To say, now I entangle, and then I do it. And then it always happens. That's a different perspective. So both options are possible. You can trust on spontaneous effects, but for the quantum computer, of course, you should not do this because then you are, well, you don't know whether it works, okay? You should really tune the things that you can tune entanglement and do this measurement and control of this quantum system in the same way. Okay, and why I'm so optimistic? The reason is that this gentleman, you know, Erwin Schrödinger, was so pessimistic. And he said, okay, it is fair that we cannot experiment with single particles any more than we can raise this Ichthyosaurus, which is dead since 70 million years, okay? 70 million, yes. So this is he says there is no Jurassic Park, okay? No way. But he is very pessimistic, see? There was Richard Feynman, he said, don't underestimate the fantasy and the creativity of physicists. Don't do this, okay? There is plenty room. Not only to the bottom, to the top, to the side, to the front, to the back, I think. There is always plenty room. Should not say this is not possible, that is nonsense. And you see, we can raise these animals, yes? See? Okay. So with the trapped ions, you can do a lot of things. You can go into fundamental physics. You got a talk by Elena on spectroscopy, I guess. Yes, I didn't attend to this talk, but I guess I could imagine what she was talking about. Measuring really fundamental constants, whether they drift or they don't drift. You learn something for the fundament of our understanding of nature. You can test whether there is beyond standard model physics, whether quantum mechanics is really the whole truth, how gravitational physics and quantum physics fit together. You need a super good way of measuring. You want to push this measurement into macroscopic quantum states because then only you can tell apart whether quantum computing, whether quantum mechanics is right for macroscopic particles. It's very hard experiments. You do it almost with the Schrödinger-Ketio experiment. But there's also this modern technology part where you are saying, okay, I'm not interested in physics. I believe all this stuff here, which is written in the books, but I want to build a new clock, which is more accurate. I just don't care about the physics. I'm an engineer, okay? I want to have a good sensor. I want to get a good clock. I have a lot of applications for this. Or I can store quantum states, or eventually I can build a quantum computer. That's now the topic of my talk. But I'm doing, of course, the other things as well. So it's not only that I'm an engineer. I didn't become a complete engineer. Two-thirds of my heart may be engineering, and 1/3 is now fundamental physics. So, but it is only coming together. You explore and control large multi-particle quantum system. That's the whole thing in any of this application or fundamental physics. So again, the menu. Now the history is over. Now comes the introduction to trapping cooling. Now we are going to be much more, regular hardcore. So that is just the intro. Wolfgang Paul. I want to tell this story here about this manuscript because you cannot read it if you're English or French because it's a publication in German language. And even worse, it is published in a in a report to the Ministry of Economics and Traffic, okay, of North Rhine-Westphalia. That is the publication of the Paul trap. And this was published in this report to the ministry, not of the whole German country, but just one country, North Rhine-Westphalia report. And that tells you, if you do really good physics, you get the Nobel Prize regardless whether you're publishing in Nature or Physrefletter or even in the obscure journal. If it's a good idea, you will get this, okay? So he got the Nobel Prize for this idea. You have a fundamental problem with trapping a single charged particle with electric fields. You cannot do it with static electric fields. So if you do the calculation, the electric potential here, and you make a quadratic potential, yeah, it has this r to the square and some coefficients on top. And then the binding force, you want to have a potential which is binding in x, y, and z, well, in the space. And you try to calculate the binding force with this quadratic potential. You get, because of this derivative, a linear force, a Hooke law. It's like a spring. The farther you pull the ion out, the better it comes back. So it is a wonderful trap because harmonic. We like this harmonic trap very much. That's why we want to have a quadratic potential. But now you try it, and you find out that the Laplace equation, this French guy is your enemy. Because if you do now the Laplace equation, then you see, okay, the Laplace equation is 0, okay? That means these coefficients of binding cannot all be negative. Some of them are positive, some of them are negative. The sum is 0. And that means you can have binding in x and y, and then you have anti-binding in z, which is of course a problem because the ion will escape. Okay, so that was the problem that Wolfgang Paul and all the people had at the time, and they wanted to do now a trapping in 3 dimensions, and it was not possible because of Laplace equation. And then Wolfgang Paul's invention was this one. You say, okay, I take exactly this potential, which is according to the Laplace equation completely right, because you have x squared plus y squared, so the coefficient is 1 is also 1, and you have to compensate with -2 for the z, okay? So that is a potential which is okay for the Laplace equation, but is of course not binding in z. And then you do it time-dependent, oscillating. That says, for some time you bind in x and y, and you anti-bind in z, and for the other time you do it the opposite. You would say, well, does this help? Maybe not, but he did it, and then you find a calculation that is the restoring force. You get an equation of motion, and you can now solve this. This leads you to a Mathieu equation that mathematics has solved before, and he found this, oh, it's a Mathieu equation, wonderful. And we can now replace some parameters. It's not important that you need know all these parameters. And then, well, it is working. I don't need this mechanical example here. I come back to this. You can calculate it with different methods, but you can just take Mathematica. That's my preferred version. You take Mathematica, plug in the equation, and let it do the job. And then you see the excursion of the ion versus the time. And you see this is now the oscillation frequency. This small oscillation here is because you are always inverting the potential with this phi of time. But in total, it's leading to an harmonic oscillation. Looks like a sine if you forget about these little wiggles here, okay? So you can now control an ion with this time-dependent potential. You have a pseudo-potential generated, which is harmonic binding. Wonderful. That's exactly what gave him the Nobel Prize. And you have just to find what are the right parameters of the DC and the AC voltage, the oscillating voltage, to make it the best. And then you get a whole, so you see, if you increase the Q, this value of the oscillating voltage, if you overdo it, you get a not so nice sign. This doesn't look like a sign, yeah? This really doesn't look like a sign. And if you really do it too hard, then you see the ion is, bam, exploding, expelled. So you have to keep yourself in a certain range of parameters, but then you get a pseudopotential which is confining. And that has been imaged by pieces of dust which are charged in a quadrupole potential, and that was exactly what inspired and also Theodor Hensch to make this trapping potential for anything. Actually used the earring of his secretary also to trap ions, not ions, but dust particles. Had a lot of fun with this. So the Mathieu equation is the fantastic way, and you find, well, this Q we already learned. If you have too high Q, that's not good, then you are out of this region. You don't want to be there. You want to be here in the soft spot here. There, the effective potential, the oscillation is a sign. That means you have now generated a linear restoring force, a harmonic binding potential, but it's a pseudo potential. It's not exactly this. If you really want to know every detail, then you have to always keep in mind it's a pseudo potential, but the pseudo potential has now this wonderful harmonic shape. So it looks like a harmonic oscillator, yeah? You can quantize this harmonic oscillator, of course. Like we know, that's the first lecture of quantum physics, to have a quantized harmonic oscillator. And that's exactly what the oscillation of our ion trap are described by. And then you build your Paul traps. You can make them from larger electrodes, this big, but you can make them from pieces of wire with a millimeter size. At that level, yeah. Pseudopotential means, it means you are neglecting this fast oscillation, which I showed here. This one, oops. The pseudopotential means you are assuming that this fast oscillation doesn't occur. Well, you shouldn't assume it, okay, because it occurs. So something is wrong. And actually, it does not occur if you are at the center of the trap. So if you're cooling your ion, this micromotion, this oscillation vanishes. Because at the very center, the electric field is just zero. So you have to cool your ions, and then the micromotion is disappearing, and then the pseudopotential approximation is becoming a super great approximation, okay? But if you are if you are extracting ions out of the trap or pushing them a lot in these fields, then you have to take care whether something happens or not, okay? So, but in the moment you're cooling them, they have a wave packet size which is maybe 15 nanometer, and the excursion to see micromotion should be 10 times, 100 times larger, okay? Okay. So these are the potential lines. You remember we wanted to have a harmonic potential. That means we need hyperbolic shapes. It stopped? No, in order to get a quadratic potential, okay? And you cannot always make these nice shapes, but you see here at the very center, even if you make the trap out of non-perfect electrodes, in the very center, this looks completely the same like there. So if you are cooling your ion, if you center it to the origin, every field is harmonic, okay? Every field is quadratic and makes a harmonic confinement. So that is a good message, because typically you are not able to make these wonderful shapes, and you fear, okay, it is not exactly the right potential which you generate, but you don't need to be worried. You have it for free if you put your ion to the center, and that's what you have to do anyways, because you want to minimize the micromotion. So that's the good news for building traps. You can safely build something. You can even take an earring or whatever. You will find all the time some place in the geometry where the electric field is zero. if you have some electrodes, well, you can do it in different nasty ways, but at some place there is a 0. And if you are now, this is now a Paul trap for one single particle, okay? And we are dealing with this place. If you put the ion here, then everything is fine. But the problem is we want to build a quantum computer. Many ions, you asked about this question. Where is this line now, okay? The line is coming now. We have a linear Paul filter, a linear mass filter, and we have this argument of Wolfgang Paul only in X and Y, okay? So in X and Y, we have now binding in X and anti-binding in Y, and in the next moment, we have it reversed. And that confines the ion along this axis, the z-axis. And there is now a node of the electric field. They arrange on this node. They are automatically trapped in the symmetry axis of this device. And that's exactly this line. If you would make it banded or curved or whatever, they would not be on a straight line. So you can shape the 0 of this electric field, and that's where you are trapping the ions. Yeah? So typically one have straight lines, and then we would say along the z-axis they are now free, and now you have to plug the ends. You have to plug the ends, otherwise they fall out, huh? Of course. So this is just the dynamic confining in this plane, and you plug the ends, where that's the dynamic defining. You have again a stability range. It's not exactly the same as for the 3D trap. It's a little bit different, but not so much. So if you are going to do a PhD in ion traps, then you need to know it. If you don't need, otherwise you say there is a stability diagram, and it's a little bit different for a 3D confinement potential as compared for a 2D confining potential. And here's for 2D. But you want to be again in some range where you have an alternating voltage and 0 offset field, okay? And then they are aligned all in this axis. Okay, and then you have to plug the ends. You have to plug the ends. This is the way to plug the ends. You just put them to 1000 volt, and then they cannot fall out to the right or left-hand side. And they are confined along a line. That's exactly the Paul trap we built. This Paul trap is actually, this is a very old photo. This is from 2020, actually, this photo. And that's what the Paul trap which I built in Innsbruck when I started in Innsbruck. So one has really to go back 2 stages of my CV to remember these things. And still they have this very trap in the vacuum. It's the same trap. They of course loaded many times ions, and they published many nice papers on this. But almost 25 years is the trap now in vacuum. Okay, so you plug the ends, you get a linear Paul trap. Now we're talking about the motions of the ion crystal. Yeah. Okay, equilibrium positions. I go through this quickly, and that is, you have this common harmonic potential. That is just the harmonic potential. M nu is controlled by the voltage, and that are the positions xm. And then you have the mutual Coulomb repulsions here. This is just a Coulomb interaction between 2 ions at different positions, okay? And then you have to find a solution of this thing. And what we do is we take these equilibrium positions first, and then we develop along these equilibrium positions the oscillation of the ions. So we say they are sitting at positions x1, 2, 3, and so on, 0 plus some oscillation amplitude on top of this. So first you want to calculate what are these equilibrium positions. And you will find then, well, they are not equidistant, exactly as we talked about, yes? So that is when you solve for the equilibrium positions, you say the forces are vanishing. The forces are vanishing. That's equilibrium. And then you get this equation here, and you just put this into Mathematica. You get this set of solutions, and then you have, for example, for 10 ion crystals, you have all these positions, and you say I have to solve for this equation, and then I get the equilibrium positions. And that is then my outcome. That's where they are sitting, okay? and you get a non-equidistant ion crystal. So this is for a specific experiment, and according theory, 2 ions are here, 3 ions are here, 4 ions, 5, and so on. And you see the distances at the outside are a little bit larger than in the center, and this fits quite nicely, yes? And they are not equally spaced here, one sees this again. So the typical distance is a few micrometer. You have hardly any trap which features ion distances below 2 micrometer, and you typically don't want to work with very loose potentials where the ions are far away than 10 micrometer or so. So that is 10 to 3 micrometer typically. And then you calculate the frequencies. Now you have the positions, now you're looking for these oscillations about the center. And what you're doing is you linearize the system. The Coulomb interaction is a 1 over something. It's not a Hooke law, okay? But if you take the approximation of small oscillations, then you can say, okay, with a small oscillation, they behave harmonic, okay? And this is a set of equations which you then can find in this paper, and you find all the frequencies in this way. So you linearize the Coulomb, as I said. If you would not do this, then you would have all sorts of non-harmonic interactions, like one phonon in this mode plus another phonon of this mode can generate a phonon of this mode, like nonlinear optics or so. Nonlinear phononics, it would be called. Yeah, you have a question?
I didn't know this so far in the mathematics. You had the boundary conditions that you're saying. So I wonder if, like practically, when you plug the ends,
Yeah.
does it add any like finite size effect or something?
Well, this is maybe, yeah, let's say here. Okay, here the electrodes are generating an electric field, and of course you need a field calculation program in order to know what the electric field is as a function of the z-axis. And this is not a harmonic. It is falling down much rapid or so. It has some properties. But the ion crystal here at the very center, okay? And there you can say, okay, here I approximate this as a harmonic confining potential. If you would fill the ion trap to the very end, so to say, you would feel exactly these things, but that's not happening, okay? So, but we know this, and we are calculating for all our microtraps now with very sophisticated methods the electric fields, and then we put the ions into these electric fields and calculate how they behave there. So this is a little bit over-sketched view of the whole thing, but and we know it is not perfectly harmonic, the potential which we are applying. Yeah. Okay, now you have your eigenmodes of vibration, and I just want to tell you what are the eigenmodes of a linear crystal of 4 ions, and you will find these arrows here. So the eigenmodes can be either all of ions going back and forth together, the common mode of vibration. The next higher mode is at square root of 5 of this frequency, and then they are breathing. That was the film, that was this video, where they are, where the eigenvector are opposites. You see, the farther they out, the larger the eigenvectors, and there are higher order modes. For an ion crystal of 4 ions, you have 3 times 4 modes, and in each dimension, in each direction, you have 4 modes, okay? So 3 times n modes in total. That's what you have. And you can calculate them, and you can compare them to the reality. This is fitting almost perfectly, and you can understand it because the ion crystal samples only the very center of the electric field where it's very harmonic. And these have been this is the center of mass mode. All the ions are going versus time here now, going back and forth together. And here the ions are breathing. Okay, that's the other mode. And there are many more modes. And actually, in the interest of time, I think I I quit this 2D, 3D things. Yes, you can do phase transitions, you can make larger ion crystals, then they are going into zigzag transitions. And I just jump over this, sorry for this. Okay. So now we talk about laser cooling. So you have a harmonic oscillator, and the harmonic oscillator is a very good thing to cool. If it would be a non-harmonic oscillator, the phonon energy would depend on the occupation number. That would be not so easy, I say. Imagine you want to cool, and you want to remove one phonon, but the first phonon is at a different frequency than the last phonon. Then you have always to keep track of what is the frequency of that very phonon to pull this also out. So the first phonon you pull out for 1 megahertz, the second one maybe for 1.2, the third for 1.4. Then you need multiple lasers which are tuning such they can pick out these phonons one by one. Now in our case, it is the same energy if the ion loses one phonon at a level of 1,000 phonons, going from 1,000 to 999, or from 1 to 0. It's always the same packet of energy, and that makes it so easy to cool. Yeah? So harmonic potential are really great. But we need this laser-ion interaction, and I tell you about this. And that is a dissipative process, so we are using rate equations. And then we can, from this, determine Doppler cooling and cooling limits. And finally, that's the typical starting point of a quantum computer. Maybe you know the DiVincenzo criteria. Initialize your qubits. And typically you want to cool them and you want to put the spins all down. And then you can start with the computing. And before the break, I hope I will be there, that I say, okay, now my quantum computer is at least initialized. I've trapped my ions, I understand the motion, and I can now initialize. Yeah? So let's go through this laser cooling thing. So we are now assuming a pseudopotential approximation. So we have a harmonic confinement and we have the momentum of the ions. So it's a harmonic oscillator. That's very simple. We know this, okay? And we are doing this only in one direction. But of course we could do it in X, Y, and Z, okay? But we do it now only in one direction. Okay, and then you do it quantum mechanically, and that is converted to the quantum world if you do these replacements. These are the creators and the annihilators of quanta, of phonons, okay? To generate a phonon, to remove a phonon. And the prefactors, this is the mass of the ion, that's the frequency of the potential divided by 2. And if you do this replacement, then you end up with this familiar quantum harmonic oscillator. Now we are really on safe grounds. I guess this is really obvious. Now you replace everything. These 8 daggers are coming in, and then you have eigenvectors which you can reduce by 1 or increase by 1 and generate phonons here. Or removing phonons, okay? Whatever you like. And this is the energy. That's the amount, the number of phonons, how many phonons are in this ion. It's a quantized levels of vibration. Instead of just an oscillation, it has now quantized level. And that's how it looks, okay? You have these quantized levels. These are the eigenfunctions here, the harmonic oscillator functions. And they have always the same distance of energy. This is h bar omega, always the same. Yeah, that's the harmonic oscillator. And these eigenfunctions are all orthonormal, okay? The overlap is 0. Yeah? Now we have a 2-level atom. We make use of a heavy approximation and say, let's forget about all the other levels at the moment and just say we have only 2 levels in our atom. And the ground state, the excited state, and that is this Hamiltonian, which has this sigma z, that means how much excitation is in the 2-level system. And this is what the laser can excite, because you can go there from one level to the other and then excite this, do Rabi oscillations or whatever. And now we're putting this together, okay? This is the other. You can express this also in spin algebra matrices. So we have learned about this sigma z already. That's this excitation. So that comes with this EE minus GG. That's the amount of excited state, so to say. But you can have also the other directions of this same operator, so to say. And then you put it together. You say, I have a two-level system which is now trapped in harmonic potential. You just put these two Hamiltonians together and you have now this sigma z, that's the internal excitation of the ion, and that's the harmonic oscillator part. And if you want to plot it, then you can say, I have now energy levels, either ground state or excited state, and I can have it with any number of phonons. And then I have this energy splitting is h bar omega, that's the frequency of the oscillator, and this energy splitting is this omega atom. So you have these two omegas. So that's the whole. You have just a direct product. The Hilbert space is a product of this and this. They don't have anything to do with each other. But now you put the laser, okay? You put the laser and you try to excite. You go from the ground state to the excited state. And while you do so, you can not only go from some level n to the same level n, but you can also add a phonon or remove a phonon, or remove two phonons, or add two phonons, and so on. And this is astonishing. I want to tell you that this is really astonishing, because if you look carefully, you see that this is a wave function which has this type of parity. And now I tell you that it goes with this red arrow up to a wave function which has a different parity. I told you before they have no overlap. Wow. This is wrong, this picture, yes? It must be wrong. Well, we forgot the recoil of the laser light. That's the only thing we forgot for this picture. So here in this picture, only the energy h bar omega of the laser light is taken into account, but not the momentum transfer. And if I include the momentum transfer, then these eigenfunctions are no longer orthogonal. That's the point. I'm coming to this in a moment. But we get this dressed level system. It's coupled by the laser. Okay, and the laser is doing a dipole interaction. This dipole of the atom is interacting with the electric field of the laser, and we call this thing a Rabi frequency. And now you can excite from the ground state to the excited state. So that is simple, yes? That's just doing the excitation of an atom. But where's the recoil? Where's the momentum? Have we forgotten this? Well, this electric field has a spatial dependence. So if I write it down, there's the electric field is E0 times e to e omega and so on. EKX. This KX here. This is in another running wave, okay? For this specific case of a running wave. And this leads then to kx here also in the exponents. Well, so far we think, okay, what does it matter? But we know that this x was related to an a dagger and a. We remember this equation, okay? And we can just take the replacement rules and now convert this x into a dagger and a, like we showed in the other transparency, okay? And now if we do, we have some prefactor, and this prefactor, no surprise, contains the mass and the frequency of the potential. No surprise. We call this now, this prefactor, we call it the Lamb-Dicker parameter. And that is exactly counting how much momentum kick is happened when you are exciting the ion. It's not only the energy changed of the state, going from ground state to excited, but also the wave packet is pushed a bit, and that makes the wave packet no longer orthogonal. So you can think of this like, I like this picture, you have a K of the laser, and this K of the laser gives a certain kick into this axis, also into the other axis, of course, and you count now the projection of this k vector into the right axis and calculate from this the amount of recoil. Yeah, and you can tailor this. So if you have just a single photon exciting it, the ion, then you have a k vector which is going this way. Just the projection is the cosine. But imagine you have a Raman transition of 2 photons. You have exchange with this k, one absorption of k1, and one stimulated emission into k2. That means the difference k vector, which is this one, would be the important k for the momentum transfer. So you can tailor this case pretty nice. You are switching into the interaction picture where you rotate the system. Sorry, yeah, it goes too quick, maybe I say, but you are rotating now with a frame of the atomic transition, such you get a detuning. That means you are no longer looking in absolute frequency, what is your terahertz, 300 terahertz of the atom and 300 terahertz plus a megahertz from the atom. So from the laser, you just count into the differences, and then you get, in this interaction pictures, you get the detuning in, okay? It doesn't change too much. You have still this recoil effects in the Hamiltonian of the interaction. Okay, and that means you have now to check this. Okay, that was now. You see, that is now. Oh, where's my laser pointer? It's gone. Disappeared. Ah, it is somewhere. Okay, but it is changed. Funny. Okay, so instead of having just D, we have this spatial dependence, and the spatial dependence acts on the vibrational states, while the electric field only, the modulus acts on the internal states, okay? And you can separate it in 2 terms. You see, one is for the motion, one is for the internal electric state. And that part is the Rabi frequency. That's done. And this part is now e to the I theta and then a dagger a. And these are different vibrational states. Say this is the ground state and this is one phonon state. And as I told you, normally they would be orthogonal. There would be just a 0. But here there is some e to the I theta a dagger a in it. And now we are doing, yeah, like typical physics, we say this is a small parameter, yeah, the momentum kicked is small. So we can say this is basically 1 plus something, because this is a small parameter, and that is 1 plus a little bit, and then we can boil it down into a more easy equation, because we can say there's this n with a 1 and an m. Well, this is clear, no overlap. Only if m is equal n. So that gives you a delta function. Where's my delta? Here, that's the delta function. But then, if you are doing this approximation and develop this exponential into something easier, yeah, just linearized it, then you get these other terms where the delta m is equals -1 or delta equals +1. That means you have overlap between wave function which would not have overlap before, and you can do the excitation. And we call it the carrier. That is the excitation without change in phonon number, the blue sideband, which means we add a phonon, and the red sideband, which means we subtract a phonon. And these terms now depend on the phonon number. And yeah, one thing is very obvious. If we are already in the ground state, that means at n equals 0, there is no chance to remove another phonon, okay? The ground state is the ground state. So here is the ground state. There is no state below the ground state. That's the meaning of the ground state. And that means the excitation from n equals 0 to n equals -1 is not working. Okay, that's clear from this equation also. And you can now use these phonons, and that is the whole trick of the quantum computer. They are a beautiful information bus along the whole ion crystal. That's the miracle. So if you have 10 ions in a string and you kick this, all of them will feel this. regardless the distance. There's no next neighbor. They can be kicked commonly, and that's the beautiful. So I try to imagine this. You come with a kick. Now you kick this a bit. This is, of course, you have to say this is now in k vector and not in x space. In k space, the wave functions look alike. Yeah, but then this has an overlap. Okay, and then you can drive it, and you can drive the carrier transition or the sideband transitions. And they are the bus, they are making these ions interact. So the Coulomb interaction is not depending on the spin of the particle, not depending on the qubit state, obviously. It's just the charge. That's a Coulomb interaction. But the kicks, they can be made dependent on the internal states. And therefore, you can use the Coulomb interaction, which is super nice and long range, and convey the kicks from one to the other side of the whole crystal and convey quantum information across the whole system. Okay? Yes, now we have to cool the ions because we want to initialize the quantum computer first. And cooling is simple. You just shine light which is redly tuned. And so redly tuned, it does not excite very frequently this level here. But it is hitting this resonance, and then from there it falls down. And this way you can pick out of an ion crystal a lot of excitation easily. Now this goes maybe too much in detail, but I will give you just the limits of the cooling. There is a complicated, well, not so complicated, but the calculation. I give you just the end of this calculation, which maybe you know already. What is the best way to cool is you're going with your laser redly tuned by half a line width of this transition. And that's the outcome of the whole calculation. It holds not only for neutral atoms, it holds also for trapped ions in the Doppler cooling situation. So you just detune your laser, this is your gamma, that's the line width, and you go to gamma half, and then you have a nice cooling. Because then you can remove with every cycle one phonon until you are in the ground state here. Okay? And that's another picture. You can say here is the transition line, the center, and you're going redly tuned, and then you are imbalanced in the sideband, and you are removing typically more phonons that you add, and that's exactly what you want. But the limit of the sideband cooling, that's this one, it is gamma half over omega trap. Now, let's take numbers. Gamma is maybe 20 megahertz, and the trap frequency is maybe 5 megahertz. So gamma over 2 is 10, divided by 5 is 2. 2 phonons. That would be not so cool. We want to have 0 phonons. So we need to have another method of cooling, and that is called sideband cooling. That is now when we have a very narrow line, okay? When we have a very narrow line, we can resolve the line. We can tune our laser exactly to this line, and the sidebands are resolved because our line is much narrower than the trap frequency. Say we have a trap frequency of, we said 5 megahertz, so we need a forbidden transition somehow, some narrow feature in the spectral response of an atom. Then you can do better than Doppler cooling. And then you are really, have a narrow line. This is narrower than as compared to the sideband separation. If this is narrower than this distance omega, then you are going up and going down. So you are always, with every single excitation, you remove exactly 1 phonon. That's the best you can do. So then it goes down the ladder, and then you are ending with equilibrium quantum numbers which are well below 1. Now comes an example, I hope. We measure how good it is 0, how good we are exciting this state here, okay? If this is perfectly occupied, then we would see that the red sideband is completely gone. If it is not perfectly occupied, if there's a little bit of population, then we can still excite something. Say we have 1% left here, not perfect ground state cooling, then with 1% of the probability we can still do excitation. So let's check this, okay? Let's check it. This is a temporary measurement. We can measure how good it cools to the ground state. We have to check whether this red sideband is really 0 and the blue sideband is still there. Then we know it is really at the ground state. Here's an example for not perfect ground state cooling, okay? But this is perfect ground state cooling, long time ago here. So you see here, that's the blue sideband, and that's the red sideband after Doppler cooling only. And I said you this about 2 phonons in the iron crystal. But if you then switch on sideband cooling, then you make this a flat line, okay? Here is no resonance. There is no chance to excite at this position of frequency. And that means the ion is now really, truly with 99.9% or whatever in the ground state of the motion. So that is now the initialization of an iron crystal. And what I told you, we need a dipole allowed transition where you have a nice scattering rate, where you do Doppler cooling. And then the next step is you want to have a narrow line, which is smaller than the trap frequency. And there are many options, okay? You can do it on a quadrupole transition, so that is dipole forbidden. You can use Raman transitions. You can use an octopole. You can do many, many different things. But you need a more narrow feature in spectral response of the atom in order to cool to the ground state. And one specific trick is now here coming. So say you have an atom and you have no chance to find a narrow line. You say, okay, sorry, I don't have the right atom, I have to change the atom. But then you can think of this. This is now your Doppler cooling transition, and you would like to have something sharp feature here, a very narrow feature. How can you generate a narrow feature? By quantum interference you can do this. You can make a sharp feature in spectral response by quantum interference. I show how this works. So you have here 2 different states. This is a transition which is brought, this is a transition which is brought, and you would say, okay, I cannot do anything. But if you put something in the dark state here, then you can have a very sharp feature. And that was shown by Peter Toszek. The spectral response, instead of having a Doppler transition, which was a very broad line, you now have these narrow features here, okay? That's just because of quantum interference of 2 transitions which are interfering. You know, you can now excite into the P state of in different pathways. And it depends on the phase of this superposition S and D. Either it's a plus or minus. And that makes this very sharp. Of course, you have to have phase relations fulfilled there. Yeah, but then you have sharp features here, even in a Doppler transition line. You can also use quantum interference here. Yeah, that's again, you can make it a lambda system as I showed you. And then you have this dark resonance here in the middle, which is a very, very narrow resonance. And that is, of course, ideal to do cooling. Here, see, this is the Doppler line, broad, can only cool to Doppler limit, but then you have a very narrow feature here, very sharp in spectral response, that goes to the ground state, okay? That's called electromagnetic induced transparency, this thing. Maybe you came along this already, I don't know. But the quantum interference of 2 transitions depends on the phase, of course, yeah? And if you make this phase right, then you can have destructive and constructive interference and a very sharp thing. And that's what we used for cooling. We used it for cooling. We have this narrow line. You see, this is a very sharp feature. It has only line width of of a megahertz or so, you easily cool to the ground state in this way. And that was the cooling. And then later, this is now more recent, in Innsbruck they cooled a whole iron crystal of 18 axial modes. So all these modes of oscillation, they have all different frequencies. You know, we calculated them. And you can cool them all. So that is before cooling, that is after EIT cooling. You see there is barely any excitation. The red sidebands are all vanished here all across the spectrum. All these vibration modes are reset to 0 phonons, all of them, okay? So that is now the initialization of a quantum register which you need to do. Then you pump all your spins into the ground state, and now we are talking about a quantum computer. That's the initial work you have to do. Trapping, cooling, initialization, okay? So we are now here. We are now here. Oh, yeah. We are going for quantum gates now. I don't know, when is the break? At 3. So we have another 5 minutes, and then I release you for the break. Okay, because I think you are waiting for the gates, yes? Okay. So first of all, talk about the qubits. So for the qubits, you need long-lived state. This alpha, yeah. Yeah, the question is what is the temperature? Yes, the temperature for a system of very few particles is a little bit an ill concept. So I better talk about the ground state population probability instead of claiming it's a temperature. Because, see, so we are cooling better than 99% into the ground state, yes? Now, the temperature will be calculated from this if you know what is the splitting of this h bar omega of the trap. So this is not super cold in the sense, because our energy splitting is a couple of megahertz, and that means there's 1% or a little bit less than 1% of probability to have this 1 megahertz of energy in the trap, okay, in the phonons. So if you convert it into temperatures, because you are familiar with this, after Doppler cooling we have half a millikelvin, and after sideband cooling we have 100 microkelvin, yeah, but it doesn't matter so much because these are quantized oscillates. So yeah, but yeah.
So like another question, like so far you've shown the energy gap between like the different phonon states are like much smaller than the energy gap from the atomic level. So like
Yes.
much smaller.
Oh, yeah, much smaller. Actually, the energy level between the qubit levels, that depends on the qubits, of course. But we are using qubit levels which are split by 10 megahertz, and our phonons are 2 megahertz, okay? In another setting, we have optical qubits. The splitting of the qubits is hundreds of terahertz, and the splitting of the phonons is, again, 2 megahertz. So it depends on the qubit, whether this statement is exactly what I said or not. I was referring more to the optical qubit. If I'm doing the qubit encoded into the ground states, then it can be also different. It doesn't matter for the gates, actually. Yeah. Yeah. Yes. This is coming. The initialization of the qubit is coming. But typically it's an optical pumping process. And you could ask, well, you cool, and then you do one optical excitation, and now it falls down. It could be heating up in this moment. But this is, lucky enough, we have the highest probability of decay from the upper state is always without change in phonon number. So that means we can cool the ion first, then we do one pulse, and then it pump into one level, and then they are initialized. So this last step is not affecting the cooling too much. Yeah. Yeah. Okay. Now we put things together, and we're looking for the qubit. And this was the initial first qubit that people used, an optical qubit. So you have a long-lived state here. The D5 half state has 1.2 second lifetime. And now you have a laser to excite between the ground state S1 half and this D5 half. The detection is very nice, because if the ion is in this D level, you can try, you send in blue light here, but nothing can be excited because this ion doesn't understand there is blue light. Only if it is in the ground state, it will be undergoing a lot of scattering events, because this lifetime is so short, 7 nanoseconds. It will radiate every second nanosecond one photon, okay? You will see it bright, as you have seen the ions. But if it is in this state, it's dark. So you see a bright, dark contrast right away from this qubit. Now comes the con. Here you need a clock laser, because if your laser is a little bit drifting and oscillating, it's not great, because your qubit will be affected. That's the reason why people go to these Raman transitions. Think of two different hyperfine states, like you take beryllium, for example, or ytterbium. In ytterbium, this would be 12 gigahertz difference. And then you have, in this case, it would be 12 gigahertz actually, the qubit difference frequency. And then you go from one level via virtual level down to the other level. So that has the advantage. These two laser beams are coming from the same laser. They can be phase locked. So that means the phase stability is great without a clock laser. But here in the hyperfine structure, you have typically too many levels. You want to have 2 levels and not 1, 2, 3, 4, 5, 6, and so on. And that is why we are using in Mainz the so-called spin qubit. Okay? Here we are so the whole quantum computer is working only with a valence electron spin. So you take a calcium-40 ion. That means there's one electron in the S state, and this electron can be either spin up or spin down, either pointing along the magnetic field or opposite, or any superposition, of course. And these are the two Zeeman states, m equals +1/2 and -1/2. And these states are split by the magnetic field which we apply. So this splitting depends then on the strength of the magnetic field. We use 3 Gauss, but we could use also 5 Gauss. And that corresponds to about 12 megahertz splitting, okay? And now this qubit system is super stable because it cannot decay. There is no state here, okay? This is a qubit which you cannot kill, okay? Has no decay channel is no decay channel available, okay? The only thing which happens, and that happens of course, is that the magnetic field is oscillating, fluctuating. Somebody's switching on the light, somebody's switching on the elevator, the magnetic field is fluctuating, and that changes the qubit levels a bit. So we have phase errors here if we don't protect the qubit against magnetic field fluctuations. That's the only disadvantage of this. And then to read it out, you convert this qubit into an optical qubit, okay? You just take this spin qubit and excite this spin up state to the D level, and then you do the traditional shelving method. The shelving method here again, this is our qubit level, the optical qubit here, 0 and 1. And if you are, say, you assume you have a superposition of alpha 0 plus beta 1, okay? And now you measure it. In this moment you say, okay, my quantum computer is ready, I want to see the outcome. I send in blue light, okay? And I look to the amount of fluorescence, and the ion will be either fluorescing, then you know it was projected into the S state, or it is dark, then it was projected into the D state. So in the moment of measurement, you open the box, you shine a laser light, and you have a projection which is alpha squared is the probability to get the 1, the 0, and beta squared is the probability to get the 1. And that's exactly what you can read out from this fluorescence. For every individual shot, you know, yes, no, yes, no. Yeah, so you have individual readout, not collective, and so on each qubit. So really the light is on or off. Yeah? Quantized fluorescence, we call it. And then we do this Rabi oscillations. So now we have our qubit initialized in the ground state, and we send in the laser pulse, and now we just excite the qubit like Rabi oscillations, going up to the excited state, and then you continue oscillating, going up, going down, going up, and now we cut the laser beam at that moment. So say, okay, switch it on for 1 microsecond or maybe 5 microseconds. And you do now, for measuring this, you do 100 times this excitation for 1 microsecond and measure always the probability to find ground state in the same way I started. Always going this way up, okay, and then projecting. And this is the projection is then here. That is how high is the probability out of these 100 cases, 20 of them were excited. Yes? Yeah, the scaling comes in a moment. That is microseconds actually. This is microsecond scaling. Yeah, yeah. The milliseconds are far down this way. Yes. No, wait a moment. This is one. No. Yeah. So we have the Rabi oscillation are typically 2 microseconds. So this is it is a millisecond time scale. Yes, that is what we have. Yes. So, but this is 0.001 millisecond. Okay. Yeah. Okay. So you excited for a certain time. You do the 100 times. Repeat this thing. Repeat this thing. Repeat this thing. And measure the probability, and this is this little data point here, or this, or this, or this. And that goes on. You can really rotate the Bloch sphere many, many times, okay? And you see at the end, it doesn't look so nice any longer, okay? And that is because your laser intensity is drifting. If you're doing 100 shots, you have always to go to the off. Not a little bit off. Higher, turn here, 1% lower, you're going there. And if you do 100, or in this case, 1,000 turns, then of course this shows up very clearly. Yeah. So that is our fidelity. We do this tomography on the gate, and that's our single bit operations. Yes, single bit operations on the qubits with the Raman transition. This is pretty record. Okay, there are not so many experiments which do it better as compared to these Raman things. We can do a benchmarking and find a few, now I would say nowadays 5×10⁻⁵ error. So in this little percentage of 5×10⁻⁵, it was wrong, okay? Very, very little error rate. Yeah? That's a single bit operation. That's the easy one. And the 2-bit we do after the break. Yeah? Okay. Yeah, welcome back. So this is the recap. Have a look to these quantum jumps here. This is the ions blinking. That means they are switching between the two measured outcomes, either bright or dark. That are the two qubit states during a measurement. Of course, the quantum computer is completely in dark when it does the operation. Then you don't shine light on it, and then you are just doing the gates. So just to recapitulate, all-to-all connectivity, because if they are living in one common harmonic oscillator, you can put the phonon wherever you like. Everybody will feel this phonon. Then you can read out the quantum states, because you can distinguish between bright and dark so nicely, to some error of only 10⁻⁴. You can also rotate the qubits. The single bit operations are really high quality, 5 10 to minus 5 in our case. And I think there's a record which is a little slightly above by Christoph Wunderlich on microwave qubits. So, but that's in the range of 10 to minus 5. So the single bit operations are pretty nice. The 2-bit operations are not so great, okay? Here we reach 99.8% in our lab, and people have reached 99.9%. So this is now what I have to explain you, how the 2-bit operations are working. And the times for the single-bit operations are a microsecond or less, and for the 2-bit operations, about 30 microseconds or 50 or so. Okay. How does the interaction between these two spins work, mediated by the common modes of vibration? You have, now I have to take both hands in order to show you what the Dirac-Solar gate was. It's just one example. There are many, many examples, but typically you make the spins interact via the coupling to the common motion. So this picture is always right, and there are different methods. There are many, many different gates which you can use, and I will explain you now one and the other. One is the historical first one, it's easy to explain, and the other one is maybe a little bit harder to explain, but that's the one which is currently used. So now we have two hands. So this is qubit number 1, control bit. That's qubit number 2, target bit. I want, if this is spin up, this should rotate. If this is spin down, this should not rotate. Okay? How can I do it? I take two ions. I send a laser pulse on the two ions, and I excite one ion. Now I can do this. That's changing the qubit level. Okay? I rotating, exciting one electronically. But I can do it also on the sideband. That means now if I excite one, both of them are oscillating, because I put one phonon in the whole ion crystal. Okay? Not only this is oscillating, there's a common mode of vibration. Okay? I excite this by exciting one ion electronically, but both are oscillating. That's very simple. But I can do also pi over 2 pulse. I just end up to excite this halfway, this way. Okay, that means I'm ending up in the situation where the first one is not excited and the ion crystal is not moving. And the other option is the first one is excited and the ion crystal is moving. Okay? Now what can I do? I can now excite the second one on the red sideband. The red sideband, we know, can only work if there is a phonon. I told you, if I have a zero population, the red sideband doesn't work because there is no level n equals minus 1. So only if there's an oscillation in the ion crystal, I can excite also the second one. If I was in this state, that the first one got not excited, not the phonon was delivered to the whole crystal, the second one is also not able to be excited. That means I'm ending in both spins down, ground state, plus both spins up in an entangled state. So that is generating a Bell state mediated with these vibrational modes. Yeah? You got this? So that is the Dirac-Solar dynamics. And here you have again the nice picture of Ignacio and Peter at that time. And we did this experiment with two ions. And these ions were stored the whole week, actually. The whole week, the same two ions. And after a couple of nights in the lab, you started to say, well, I call my control qubit Peter and the target qubit Ignacio. Okay, so you send this laser pulse. The first one you send here, you excite the motion together with the electronic excitation, and target can be only excited if there is a motion. So that's exactly what I explained you with my two hands, yes? And actually this gentleman published this paper, really a seminal paper in 1995, and they said, it is great, this is the super system to make a quantum computer. You can do these gates, you have basically no coherence, you have a perfect detection efficiency, And something was wrong. Look, this is when theoreticians are publishing a paper about an experimental proposal. This thing is an ion trap, okay, maybe. And these 3 dots, they tell you it is scalable. Yeah? It is not scalable. Yeah? It is not perfectly scalable. These are the 3 dots. So everything is right. It is scalable, but only to a certain degree. That's what I want to say. It is not scalable to the level where you can really say this is the gate for a quantum computer. The first point is we have to cool the ions to the very ground state. With my dynamics, if there's a little bit of residual phonon number, that leads directly to an error. That's why it is called a cold gate, okay? You have to, if you are doing 99.9%, you have an error of 0.1% with a gate. No question, okay? So that is a problem. You need to cool a long ion crystal of many, many modes. We talked about this. 3n modes. When we have 100 ions, we have 300 modes. And if there are some phonons and they mess it up, we have a problem, okay? Then the other problem is the recoil. The recoil from the phonon, from the photon here, this laser, which hits this ion here, bam, gives a certain kick. But to a single ion, I've calculated it for you. That was this eta. If you now have 100 ions, this is much more heavy, okay? Very easy. It's just 100 ions are more heavy to kick because you have to kick all of them, okay? This kick is very small. Or the other way around, you have to take more laser power. Or the other way around, you have to take longer interaction times. So if you have more ions, it becomes much harder. Then third problem, we have had all these vibrational modes. They have all different frequencies, but this spectrum, you know it maybe from solid state physics, it becomes almost a band of vibrations. Then it's very hard to select one of the mode and don't touch the other one. So you are not exciting only this one gate mode, but some other modes are parasitically also excited. Not great. That is a spectator mode called, and they affect the gate fidelity. And last not least, if you put 100 ions as a linear ion crystal, this undergoes typically a zigzag transition. I couldn't show this because of time, but there are phase transitions in the ion crystal which make it a 2D or even a 3D crystal, and then it's no longer so easy to handle. Okay, so these are all problems with the scalability. So that's the Dirac-Solar architecture, or linear ion crystal for a quantum computer. And that's the party that was the Dirac-Solar gate, and we made fun of this because the gate means also in German Gatter, that means a door, okay, or a door for animals, okay? And it's very shaky, that because it was not so stable at that time, the fidelity was not good, it was extremely wackelig, okay? So that's nice memory from that times. And now I told you there are many other gate operations nowadays available. So the Dirac-Gatter was historically the first, but now people do this Möllmer-Sørensen or spin-dependent light shift gate, and there are many other gate operations. So that is good. You have maybe a gate which is good for this qubit, or a gate which is better for this operation, and so on. So there are, it's not only that there's one gate for trapped ions, but there are many gates. And I like it because that gives us more leeway. But I like most the spin-dependent forces, and that's what comes now. Don't be frightened for this, sorry. But we have a standing wave, okay, composed out of a lin-perp-lin configuration. We talked in the break a little bit about lin-perp-lint. So you have a standing wave, but in polarization. The waves are not going opposite, but in a Raman configuration, you have a standing wave where the polarization changes here in this direction, okay? And what does it mean? Of course, if we excite from a certain m level, it makes a difference if it is m equals plus 1/2 or m equals minus 1/2, whether the excitation is possible or not, because that's the Clebsch-Gordon selection rules. So the light shift is very different depending on the spin orientation. You have a question?
Question about the previous slide. You showed there's like a lot of complicated cubic gates available. Are you aware if there's any algorithms which have a complexity speed up on like such a design compared to other designs of qubits?
I didn't get it exactly, but I have to come a bit closer and listen more carefully.
So we have all these qubits, or we have all these gates you can apply on your design.
Yeah.
Are you aware of if there's any algorithms which are faster on such a computer or have a better complexity compared to other designs of computers?
Oh. Well, our quantum, well, the trapped ion, you want to compare trapped ion with other quantum computers, yes? So the asset of the trapped ion, there is a transparency on this actually. I think it comes here, sorry. Here, this is my transparency on this comparison, okay? So if you have trapped ions, you have the best fidelity ever. You have best connectivity ever. You have the best detection time. You have the longest coherence. This is absolutely unbeatable. The neutral atoms have the very nice number of qubits. Rydberg, for example. They have not these long-range interactions easily. The superconducting qubits are about a factor of 1,000 faster as compared to the ions. But they are doing a little bit messy, okay? I would say in the other way around, they need to be 1,000 times faster because their coherence times are so bad. But they can also be 1,000 times faster. I don't know whether it's an asset or a con. If you have now a classical computer which wants to read the result of a quantum computer and feed back, then you need a very, very fast control electronics. Maybe you don't like it. Maybe you want to have a control electronics which is acting at a microsecond range, and you don't need something which works at a nanosecond. You better have it at the nanosecond for superconducting qubits. Where the photonic devices are maybe exactly the right things if you're building up networks of interconnected computers or so, and I have no idea whether well, this is of course for the solid state. Maybe in a future world we are able to connect a classical hardware right on the chip with a quantum hardware right on the same chip, but I think that is pretty far that we can integrate it so densely. But then these solid state things are great. So that is my personal, but that's it, okay? Okay, let's go for this spin-dependent light force, okay? We think of a spring, which that's the harmonic oscillation, and you can excite this motion. By an optical standing wave, which is slowly running underneath the ion. Okay, so that means if this wave is not static, but the frequency of the two laser beams is different by exactly the resonance frequency of the oscillation, then after a while the ions will oscillate even further, and so on. So that's what you don't want to do. You want to detune it a tiny bit of this resonance frequency, of this resonance condition. What happens if you have just a Kinderschaukel, okay? You're pushing it periodically, but not exactly at the resonance frequency, but a little bit off. What happens? First you excite it, but then you're coming out of phase, and then you're de-exciting it. So in phase space, that looks exactly like a circle. You're exciting the oscillation until you come out of phase, and then you're de-exciting it. So these are the phase trajectories of an ion crystal of two ions, but they are depending on the spin orientation. If the two spins are pointing up, you can excite this motion. If the spin's pointing up in opposite direction, you cannot, because this force is opposite to this one. This is also doesn't get any excitation because the forces are compensating. This one is doing the other circle, this one is doing one circle, this is doing no circle, this is doing no circle, okay? In this way, you can make a gate because you have to make this face here now exactly right. The circle should enclose a face, and then you have a so-called Berry face, which is affecting your quantum state here at this place, at this e to the I phi. So these states where both qubits are showing the same direction, both down, both up, they get the phase, this ones do get no phase. So you tune your parameters of your standing wave, polarization gradient thing, that they excite this exactly. After the whole gate, the vibrations back into the original state. And here comes the great message. This is a hot gate. It means you don't need necessarily to be in the very ground state. You just can start a little bit off. It makes still the same circle. You start a little bit off, it makes the same circle. So that is, of course, much nicer as compared to Ignacio and Peter's proposal. So we take this one all the time, and we make it even better, because now, as I said, there can be phase fluctuations of the laser, there can be all sorts of problems, and maybe you heard about spin echoes, which compensate for this. So you do something like here, and then you flip, and then you do exactly the other way around, and we are doing it robust in phase and duration. So if our laser pulse or intensity is not very perfectly chosen, then you would go not a perfect circle. You don't come exactly to the same point. That was the problem, you know. You have to have a laser intensity stabilization which really brings you exactly here, okay? And if it's 1% off, you feel it. Now you can make it in duration or amplitude stable by a very nice trick, because you can make 2 loops and they are compensating then. If they are not completely closed, the combination of them is closed. So they are not closed, yeah? They are bad, but if you do it right, the end is still okay, okay? That's great, isn't it? So in this way we can be double magic somehow, okay? That's how we experimentally implement it. And then we are exactly, we are robust in duration or excitation of these modes and so on. And then we do this benchmarking. So here are the hours. These are the hours, and you see, wow, this is the gate fidelity, and slowly it drops, yeah, because some laser power goes down or some magnetic field is wrong or so, yeah. But we do benchmarking and we test everything. Our most dangerous enemy is the magnetic field fluctuations. So we have mu metal shielding, we have active shielding also. We try to compensate for bad solid state physicists which are in the basement. They ramp a 13 Tesla ramp up and down this. Yeah, you know this. These are the people. Yeah. Okay, we had this already. Now we come to the architectures. The architectures are required because you cannot have an all-to-all connectivity for a 1,000 qubit operator. For 1,000 qubits, all-to-all is just, the other expression of this is a big mess, okay? So like in a town, you have the small streets going to the houses, but the larger streets connecting the small streets, and then some highways connecting the big towns. So you need this architecture in order to have a high number, still a good connectivity, still at a good fidelity. And that's how you connect the number of qubits with the controllability and the crosstalk and the dephasing. And only that can boost the volume. So that is exactly the problem of the IBM Google. You have a static connectivity, which is just with its neighbors. Okay, you want to have a little bit more. So it's always to find compromises, yeah? And here is an example of a solid state proposal for NV or vacancy-based quantum computer. It's a nice scheme which shows you how connectivity can be working at different levels. So here are the qubits. These are these NV centers with the nuclei around. And these nuclei are controlled by the NV centers. So you see a couple golden, and there are smaller golden ones. So that is already a connectivity here. And then you have all this controlled by radio frequency here, addressing in frequency. But now you have, say, a bunch of 10 qubits here sitting, That's not good enough for a quantum computer. How connect this bunch to this bunch to this bunch? You can do it with optical cavities maybe. You bring them all in optical cavities and then you have an optical response which is then connecting these different things. You need to implant them, yeah, in order to make this, have a very special way to build this, yeah, okay?
Maybe I understand this wrong, but in the beginning of the talk you said that the advantage of such a quantum computer is that the ions are all the same, right?
Yeah.
Yeah, made by God. I like that quote. But in this architecture, you would have, it would depend on the
Neighborhood, yes, absolutely.
fall a bit away, right?
Yeah, no, I just give you a couple of examples for all these different attempts to build quantum computers.
No, I don't need to
Yeah,
pick on you, but
yeah, no.
of curiosity.
No, absolutely. Here you have the problem that all these NV centers will have a little bit a different magnetic field, a little bit a different shift and so on. You will certainly suffer from this, yes, absolutely. So in reality you need more electrode to compensate for this, yeah, absolutely. It's just a sketch. It's very much more complicated. But what I want to say, you can have this interconnectivity here around and then connect these bunches in big goes. The other way to show you what is not the future is this wiring. So these are two gentlemen sitting in a cryostat. This is a dilution fridge. It's meant to be 10 millikelvin here. So it's so huge. It's this big, okay? Wow. Just making bigger is not a solution, I think. The connectivity problem is another problem. See, all this, every qubit needs a lot of control wires. They have to go down. In the trapped ion business, I want to advertise this, you have just laser beams. You can switch them on and off. They are gone if you don't use them. There's not a material piece left which injects noise and all kind of problems. So that is now the two architectures of laser-driven quantum computers with trapped ions. First, the linear crystal processor inspired by the Dirac-Sol proposal. So the qubits are sitting here in a linear ion trap, static, and you address them with laser beams and play with the qubits 1 and 2-bit operations. This is strongly put forward by two companies, EQT and IonQ. You see the bosses there. And it is also by the Innsbruck group. So we did the first addressing. We steered a small 2 micrometer focused beam on the ion crystal and could hit this one, this one, this one. And people told this a heroic effort. Now it is an architecture for quantum computers. Everyone does addressing, yes? The other way is Dave Wineland's proposal. He says, well, should we not take only those ions into the laser which we really need, and the other ones should be shuttled away. You need a lot of segments. This is not one ion trap, it's typically 50 ion traps nested together. You can make a potential well and move the ion in this potential well. You can also separate ions, you can merge them, you can rotate them. So you handle only those ions which you really need, and that makes the scalability in principle possible. Okay, in principle. But of course you're ending up with a lot of shuttling and a lot of mess to build these devices and to operate them. But this is now a pathway to ultimate scalability. Now you just handle those qubits which you need. That makes this mode problems. The radical way is you take only 1 or 2 ions into the laser and the other ones are waiting at the side. And if it is on the algorithm their job to do now this next thing, then they are doing this job, okay? Then you shuttle them in, you do this, and you shuttle them back. So this divided emperor. And we did this, okay? We have only 2 ions in the laser interaction zone. Here we can do the gates, here we can do the readout, here we can do the single-bit operation, 2-bit operations, and then we can merge ion crystals, we can separate, we swap them. And this is what we did in Mainz over the last years. With this, we could also reach this fidelity on the gates. And that is just how the computer looks like when we operate it. We're not sitting in the lab, but the lab is just next door. We are not standing in front of the apparatus. And that's the maximum of entanglement I want to show you. So you start with one qubit in the superposition generated by this Hadamard. And then you use this superposition to control the second one. Now you have a Bell state. Now you can shuttle this ion out of the way and you bring a new one in. And this new one is now on a controlled knot with this one. That means this was in the superposition. You're knitting entanglement, so one by one. Always you bring out of the place. You bring the new one, you bring the other one out of the place. Yeah, every time you have to shuttle. And you send in this Kiskert circuit, and then our compiler can optimize the circuit and then make a shuttling protocol out of it. The compiler then tells the hardware what voltage to apply to bring exactly the right ion into the exactly right position. And then it's executed on hardware. And that's the result. So that's a GHZ state of 6 qubits. And see, there is a little bit of errors, but very tiny little bit. Huh? So that's what we do with a full shuttling. Just to say, this is like trying to play Beethoven with 2 fingers only, okay? You know, maybe if you don't play piano, you play with 1 finger. 2 fingers is also not very much better, I would say. So with 2 fingers playing Beethoven is impossible, okay? You play all the keys, but it is very not a great melody. The other way is you have 1 hand and you're playing only these 5 keys, which are underneath your fingers. That's also a poor melody. You cannot play Beethoven with this. That's why the pianists move the hands and they play with the fingers. If they want to do fast, they do it with the hand of the fingers. If they have to cover the whole range, they move the hands. We don't move the hands, we move the keys underneath the fingers. That is joining this shuttling process with individual addressing. So we're shuttling not single ions, but whole bunches of ions, like a train of qubits going underneath the addressing unit, and then it's resorted, and then the next train is coming to be executed later. And that takes a lot of shuttling effort out of the game. That is much, much faster, can lead to much higher qubit numbers at the same level of accuracy for the gates. So we have to fabricate now these traps. Now comes a lot of pictures. We got from the BMBFs the money to make out of this empty room a clean room in only 1 year. And I think if I talked to somebody about the Hamburg, not here. Well, that's exactly the problem. Normally it takes years, okay? If you ask a Bauabteilung, you know, German administration, oh, very serious. Nothing happens, okay? We just ordered the room and we installed it ourselves, basically. So this is now full and functional, and we can really in-house make, within a week, we can make these ion traps. I have one for you here, but you have to give it back. So this is from the clean rooms, from the clean room here. It's a gold. You start with a glass wafer, and you shine laser pulses. These laser pulses, they weaken the glass. It looks a little bit white, and you can find this tourist souvenir stuff, the Tour Eiffel in a piece of glass or so. This is the same process. And then you put this into wet etching, and then you make these structures. You see, these are really structures, and they're 3D sculptured. You can really go into the glass, and then you have this to be coated by gold, okay? And you know the structures which you make are undercuts. Undercuts are really cool because when you coat it, there is still a piece of isolation. You can have different electrodes with different voltages. And that is a 3D structuring which features all this kind of complexity which you need for an ion trap with many, many qubits. So some examples. You see these corners here with your naked eyes, there's a little undercut here that prevents from having shortcuts. So it's all very nice. And then we coat it with gold, and then we have to assemble it. Well, these are stacks of different layers which are put together at a precision of 1 micrometer. And yeah, this all takes only a week altogether. You start with a glass. This is a fast process. Then you have to etch it. This takes a little bit longer. Then you put gold. Then you bond it together. You have maybe some inspection by microscopes. And then after a week, you are ready. So people ask me, this is your week? Yeah, we are working day and night. Okay, yeah. Okay. So, yeah, this is just a film. I hope this runs, because that's a short tour through the clean room. Yeah. Yeah, we're going through the clean room, and that's now the etching process. We can see on the monitor how the laser goes through this. And you see this table here where the piece of glass is sitting. And then you take it out. It looks like this whitish thing, but it's still a full piece of glass. And then you etch it in KOH, and then it looks like it really has everything which was white was removed, okay? And then you put it into the coater here, and then you put gold on top of it. At that time, we had not the wet bench here installed, so it's still a hole. Yeah, that was in this moment. Yeah, and then you assemble it. So we're very happy. Actually, the next transparency shows you our, our trapped iron, trapped in our own trap, the first time. A week of trap fabrication, bake out, vacuum, the great thing is we don't need to ask different suppliers, one for the gold coating, one for the bonding, one for this, one for this. After a year, something failed and we can start at scratch again. So that is horrible. We have it now all in-house. We can do it just like this. And it works. The trap looks very nice. And the long-term design changes, we can now play with the architecture very much, because a very short repetition time to have a new device. And I tell you just a little bit for your imagination. So far, we're building this piece of a quantum computer, okay? But if we want to scale it up to 1,000 qubits, and that's necessary, then we have to do this vias, these junctions here, X junctions. You see it magnified here, to shuttle the ions across. And then you would have some laser interaction zones here, and another one here, and another one here, and shuttle in the whole. This is a sketch of this X junction here, how the design looks. You see how 3D this is. This is really a full 3D structure, which you never can fabricate in a conventional clean room. In a conventional clean room, you have a nanostructure, but everything on a surface, nothing is 3D. Here you can do a 3D structuring at a precision of 1 micrometer, which is exactly fitting to our demands. Okay, so now we come into the optical and electronic control. Some question on fabrication? No? Yeah?
But these three-dimensional structures, how exactly do you make them? What kind of challenges in comparison to the normal conventional?
It is much, much easier to make layers. Yeah. That is what people do in the clean room now for decades. And every clean room is equipped with all the instrumentation. But say if you have two parts of the trap, you want to assemble them, or you want to integrate some micro-optics even. Everything there has to be accurate at the micrometer level. And then you have a flip chip bonder, you have kind of all this kind of machines which allow for adjustment at the micrometer level. And full 3D control, that is really challenging, I tell you. But we are through this now, so we can handle this, and the alignment is near to perfect. The other point is we have all the processes in our clean room. That means we fabricate the trap, we assemble it, and we put it in the vacuum system in the clean room. There's no chance for any piece of dust to fall on this ion trap. And the dust is well, I could say dust is typically an electric isolator, okay? That is the awful thing. If you have been growing up with the old TVs, the old screens, they always are dusty. That is because they are attracting dust so nicely because of the voltage that's charged. Yeah? And that is exactly the same thing. We have a voltage and the dust is sticking there forever, and the dust will really affect the electric fields. It affects so much the heating rates. So if you are not an expert on ion trap fabrication, I tell you how you can immediately tell it's a good or it's a bad trap. You just look on it. If you see naked isolator somewhere, if you can look from one angle and see, oh, there is white ceramics, then the ion can also see the white ceramics. And then the thing is bad. So it should be always hidden, the insulator, somewhere that no stray field can be ever seen by the ion. Then you have a stable electric field configuration. So that is also very good that we put it in the vacuum. We have no additional dust, no problems, and we just take it out when it is completely at vacuum and no further problem. Yeah? Well, the shuttling process is pretty 100%, absolutely. So the losses of qubits in the algorithm happen if we are doing, well, the most problematic are the double wells, I tell you. Not that we lose the ions, but that we want to split an ion crystal, one is going right, one is going left, and it's a very subtle balance, okay? You can think of this. You have a double well potential. If it is a little bit deeper here, both of them fall here, or both of them fall here. So this is the most critical operation, the double well formation. This happens sometimes that both ions going to this side and you don't want it, okay? This is what is that has to be calibrated because it depends on all these little stray voltages, which we had before not so good under control. So every other hour you have a calibration, you find the perfect arrangement for having the double well perfectly symmetric. No, the tilt voltage optimization is called, and then it's running for the next hours safely. But then the parameter is going away, and then you have problems. That is what happens typically. Ion losses are not at all very frequent. For the very deep trap, which I showed you at the beginning, we had ions, 2 ions in the ion trap for a week without any loss. 2 ions for a week. Now with a larger ion crystal, yeah, it happens a little bit more often, but that is typically not a problem. Still, we record at the end of every computation shot, we count the ions. So we are really counting, and then we do a post-selection. If something falls out, okay, we drop the data and load new ions, which is also a fast thing. It happens in a fraction of a second, yeah.
Just a question also about the shuttling. Are there then multiple parallel tracks in order so you can switch the order of the ions, or are they still all on?
Yeah. We at the moment we can just turn the crystal actually. We turn the crystal without going to another detour and multiple tracks. But you are right, in principle we would like to have multiple tracks. Now we have this linear arrangement only, but now with the clean room you can play much more actually. Yeah. Okay, this is the optical control, which it should not be, okay? That is the view on the typical optical laser table that everybody has who does optical experiments in atoms or ions, and looks beautiful, and people typically make a photo of this and say, this is our quantum computer. No, this should never be a quantum computer like this. A quantum computer should be tidy, no optical table, no adjustment, no screws, no nothing. It should be engineered, okay? This is much more closer to a real quantum computer. And here you have racks, everything is only fiber coupled. We have so-called laser processing units. That means a little piece of optical table shrinked by a factor of 5, actually by the engineers of the company Toptica, made it much more stable in time, so you have not to readjust it every day, every week, just fiber couple, full, done, okay? this is the view into our quantum server room. It's a little bit, quantum server. On the one side is electronic control, on the other side is optical control. Now it is much more full as it was. These are optical modules which steer the laser beam into the ion trap. Here you see more above of this. So you want not to have any optical tables, you have fibers and then fixed mirrors and adjustments which have little degrees of freedom. The little degrees of freedom which are still there are motor controlled from outside. So you can adjust, you have some monitors, they have automatically adjustment routines. Actually, you can type into the Python code, optimize, and then it does, first it gets an ion, it adjusts all the laser beams, where there are motors, boop, 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 they find the right spot. It adjusts all the frequency of the lasers, it adjusts all the pulse lengths, all the detunings, whatever, everything is adjusted. The voltages of the trap are adjusted, the cooling is done, and then a 2-ion crystal is loaded, and then it's characterized whether the gate is working, the single bit and the 2-bit, and then it says done. So it's kind of a start-up of the quantum computer with the auto-adjustment routine that takes now only 10 minutes instead of the students spending the whole day on this before. Yeah. Now you just run Python code and then it produces this state. And then you can start with your research. You have a question? Absolutely. This auto-adjust is pretty fast. It takes about 10 minutes, as I said, yes. Absolutely. The reason is twice. First of all, the mechanics. Second, we make everything from titanium. You remember our most evil danger was, the evil enemy was the magnetic field fluctuation. So everything there is made from non-magnetic materials. And I went to the waveguides already. That is a pretty fast. Okay, here. Well, one part of the addressing optics is in the vacuum. That's a lens, a spheric lens, which steers the beam on this slit of the ion trap, which you have in your hands. And then you see there is an external addressing optics from Fraunhofer Institute, which features 10 beams going into 10 positions, which are coinciding with 10 ions. So that's this hands of the piano player. And then we add this shuttling to change the keys, okay? This is a detailed view of the addressing unit when it was under investigation. You see 10 fibers coming in the photonic waveguide. That makes these 10 foci, which are then steered all the way down here on the ion crystal. Yeah.
Are the magnetic fields generated by the motors that control the optics?
Yeah, we have, yeah. It is super dangerous. You have to think of everything, absolutely. We became pretty, at some level you cannot avoid every magnetic field, but we have tried to make one setup which is really adjustment free, yeah? So there you have no free motors inside. The one which so it's going in steps, basically. We have, it always, if you know better how to operate, then you can leave away some degrees of freedom and say, I can now make it so nicely engineered that it will not drift away. But just to say, that is the quantum computer, I build it, I know how to build it, it's impossible. We need to do this trial and error, and at the moment we have some motors in some setups we don't. So I go to this in a moment, actually, because we have very many parallel experiments going on for all these different aspects. But let's go to the laser control. For the laser control, you have now, say you have your addressing unit with 10 beams. Each of this beam has a special frequency, detuning, of course, laser power, and it's switched on and off. And that means we need for each of this beam an acousto-optical device. So we have 2 addressing zones. That means 20 of these beams coming from fiber, from modulators, AOMs. They need their radio frequency, okay? They need to be controlled, okay? Then we have this, on this trip which you have 50 segments. So you have 50 segments on the top, 50 segments on the bottom. That means only 100 wires going to this to control the shuttling. We need the DC control for this, all voltages. They should be also pretty noiseless, actually, because if we put noise, then we cannot cool it good. So there are many of these boards which we built, and they are typically here in this electronic racks together with the compiler, the optical control, and the 3 times shielding of this mu-metal shields here for a titanium vacuum chamber. And that is our demonstrator setup, so to say. So, well, I go through this, that is really not important. Now you see there are these boxes in the room, which you have seen before. In the boxes there are these magnetically shielded and made out of titanium vacuum systems. And it is really, as you say, it is really horrible. If you look for magnetic properties, well, you have an iron getter pump, okay? Whew. This has a magnetic field. So we put it to a long tube. Yeah? You have these getter materials. They put it together with stainless steel screws. These stainless steel screws were unfortunately no magnetic skill, just an ordinary. They save just €1 on this, but we have to replace it. So this whole holder is from carbon and copper. So these are all the techniques. And this is now what the whole layout is. We have at the moment these 2 traps in operation. This one is used, this one is set up. This one is used the whole time for establishing some quantum algorithms. We can only operate on 6 qubits because that does the radical shuttling approach, so we are ending with 6 qubits in this one. Still, we can test the whole software and control hardware on this one. This is the shuttling combined with the addressing. This one is in operation. We have trapped ions, but we have not implemented the quantum algorithm on this. Meanwhile, we are setting up different apparatus with different types of integration and going stepwise to a more robust operation of quantum computers. That is exactly, some of them have more, they look alike, in principle they are, but they have different control architectures around. We have also a cryogenic trap here. I mentioned this because all of them are room temperature. So if you are talking about the trapped ion quantum computer, they can do good fidelity gates without cryo. But eventually, we talked also about qubit losses and collisions. If I lose 2 ions in a week, okay, and I need 2,000 ions, that means I have to make loss rates. I will see loss rates on 2,000 ions, which are 1,000 times harder than for 2 ions, obviously. Because the chance to lose this one and this one is completely independent. That means if I stated, well, we had these 2 ions for a week, this is great, this is good enough. It's not good enough. It's not good enough because if you think of 1,000 ions, you will use this crystal, one of them, after 1,000th of a week, and that is too early. Maybe you are really loading and finding this problem and every time, yeah? So that is why we want to have cryogenic vacuum in order to reduce the loss rates further, yeah? For really large ion crystals. Okay, addressing unit, external addressing, I talked about this. This is the shielding, actually. As Helen, she is very happy because she measured for every shield independently about a factor of more than 50, 60 of reduction. So 60 to the 3rd power is our qubit protected from the outside magnetic fields. And this is a major improvement to our current setup. And that will make our qubits, instead of 2-second lifetimes, now hopefully a couple of minutes lifetime. Now we had this optical and electronic control. Now we talk about the software stack. Software stack is super important. I underestimated this. I'm coming from physics. I thought the physics package is the whole quantum computer. It's completely wrong. The quantum computer is the whole stack. There's a little bit of physics package, but then there's an operation system, there's control hardware, there's all this kind of software and compilers, and that is coming here. This is our operation system if you are a PhD student, you have to learn what this knob is for, okay? Horrible, horrible. I don't know it, actually. I have to say, I don't know it. So nobody can use it. If after 2 months you know how to operate it. Can operate anything. Now it's like this. You have a Python code. You can import the circuit. You can just run the circuit. Yeah, you get the output. Everybody can do this one, okay? But this is not so easy. This is not immediate, yeah? It's a long way between this and this. And yeah, that's the life. You see, Janine Hilder now implemented this qubit circuit. While she does it on the Python, here, the thing is happening. Huh? You see it on the controller. That's the controller. That's really. And now the 2 ions are doing the job. They're doing this gate here. Okay. I don't know. They are still working. You see, they are sometimes blinking. That's just to check whether they are there and whether everything's fine. And then comes the output. Blah blah blah. It gets the data out. Actually, we can run this Python script from any place of the world. Yeah? And then, finally, come on. You see the quantum computer is a little bit slow. There will be an outcome. Maybe my computer is also slow. Is it still running? I don't know. Yeah, it's still running. Okay. Well, now comes a histogram. Okay. So that's a Bell state, the one I showed you, 0, 0 plus 1, 1. And these are the errors. Oops. And so you can immediately run this from any place of the world. And you need to operate it in Python, but you can use any other optional hardware or other control software. And that was starting in 2021. This is now a really long time ago. The president of University Mainz asked me, Ferdinand, could I show something from your quantum computer? And I said, yes, welcome. But I want to show it in Berlin, because of the celebration in Berlin, not in Mainz. Oh my God. Then I said, okay, we have to do a live operation. He should present an entangled state in Berlin, which he generates, okay? And that was the Parlamentarische Abend, evening of the parliament. So that's, by the way, the head of the DLR here. Very important people. I was super nervous whether this works. And that was now the moment. They were there. I have to switch on the. So that is the president, and he said that was the drag and drop interface. He could drag the. He would. Okay, that is now what he does. He puts a ZZ gate, Hadamars, and then he. That's the simulation. What should be coming out. And that's this Bell state. And he. Yeah. Yeah. So that's our president. I was super nervous, actually. Yeah. And then, and he did it, and then the answer came. Okay. And that's the same. Okay. So to say it, you can address it either from the drag and drop interface or from PennyLane or from whatever language you like. Then it is validated that you can enter the quantum computer. We had a lot of attacks on our quantum computer. This has an own network node and own protection. Any quantum computer should have a very secure firewall. And then the circuit is optimized, composed in the shuttling and sequence, and then executed. And this can be done by colleagues from us. They are asking for a playground, okay? And in reality, this user interface has all these options here. User management, job system, so you can make a list of users with different priorities and so on. The high-level stack, what we call it, there you translate the gates into native gate set, you optimize it with respect to this, with the PyTCAT, and some other additional compiler features, and then the shuttling. And the low-level stack, that is now addressing our control optics and control electronics, like in a regular computer. And here see a specific thing that is very important for variational quantum eigensolver. So you need for this parameterized gates. So you tell the quantum computer, I want to do a single bit rate. I want to do a single bit gate, but I will only tell you later whether it is this or this or this, okay? I will change this parameter, but you should compile it, and then you get the number, and then you do this one. And you get another number, you do this one. But you still have the same program, only with this variable updated. That is this parameterized gates. So you have this A over pi pulse. It's not a pi over 2 or 2 pi or whatever, but it's A, okay? And also this gate has a parameter C. And then only later, after the compilation, you update these parameters. What do you want? A pi or 0.7 or whatever, 0.03, yes? Yeah, and then you do it. Why is this important? It's important for this variational quantum eigensolver application. There is a classical computer, has a certain Hamiltonian with certain parameters. This is casted into an unitary evolution of the qubits. And these thetas, these are exactly depending on these angles here, which you have. So there are all these theta e's that controls the unitary evolution. And for each of this unitary evolution, the quantum computer should evaluate the energy and then give back the expectation value of the energy. And then the classic computer can optimize and bring it back again with new parameters. You don't want to compile all the time. You want only to update the parameters. That's the reason for this. And that we can do. We can then see this shuttling compiler. Out of this, it does this shuttling. Yeah, here these two ions are entangled here. This is a correct phase gate here. You have to bring them again back together, and you see how many shuttling steps are used for just this very shallow and very poor and small algorithm. You need already so many shuttling steps. So that's the reason why we like this. That was on this one finger addressing. If you have more fingers, ions per segment, if we have only 2 ions per segment, we need about 60 shuttling for a 20 qubit operation and 1 gate. So we have to shuttle 60 times more, 60 times more before do a gate, yeah? The computer is basically only shuttling the whole time. In our case, with 6 ions, in the application of quantum error correction, it was 90% of the time shuttling, 10% time of the gates. The Quantinuum company, they did a little bit a deeper algorithm on more qubits. They ended with 99% shuttling and 1% gate. That's not the way we want to go, yeah? If you think of a 1,000 qubit operator computer, you never end, okay? And that's the reason why we need this addressing, yeah? Addressing plus shuttling. That's really the architecture which we want to have. Now, another point, you want to read out maybe some of the qubits and keep the other one intact. A syndrome measurement, or you have a decision. If this qubit is 0, I should do something with this qubit. If it is 1, you should do something else. That's what we can do. So we can, here you encode a state by some gates, and then you can measure here a syndrome, but you keep the other qubits okay. You don't touch them. And now, depending on this classical information, you do some rotations or don't do them. So if the qubit is 0, you do an X. If it is 1, you do an X not. You don't do an X. And that means you can now do a real-time decision logic. That means you have to have, in reality, you have to have a counter, you have to have a FPGA which makes the decision and decides, well, here was an outcome, I should now do this or this, okay? That is not so easy. And here it is shown, just you bring a qubit in the superposition, you measure it, in half of the cases you get 0, in half of the cases you get 1. If you get a 0, you do nothing. If you get a 1, you rotate the second qubit. So you get always with the first one was 0, the second one is also 0. If the first one was 1, the second one got rotated and then gets 1. So that is a very simple thing, okay? But we did much more complex ones also. Yeah, and then if you go really eventually to a large register with his 2 hands operating on the qubits, think of this. This is now the whole trap. Here are the ions. This is a processing unit with 10 ions or 5 ions sitting here. Here this is a storage unit. That's another processing unit. So here you can send laser beams in. Here you can laser beams. And here you have to resort the ions. And now the question is, how do you sort the ions such that the algorithm is really executed the best way? For solving this problem, you would need a quantum computer. You don't have a quantum computer if you don't solve this problem. So, but fortunately, there is a greedy, maybe not optimal algorithm, but it's at least scaling nicely. So we are doing an approximately holistic approach, a holistic and heuristic approach which sorts the ions. And I show you because that's fun. This is the test random circuit, okay? And you see you have interconnectivity. Wow, it is hard. This ion should be connected to this one. They are not sitting next to each other. So, woo, you have a problem, okay? If 2 ions are sitting here, they are sitting in one addressing zone. That is easy. You can address immediately. So what do you do with this? You have your qubits. These are the idle qubits in the storage stores. They are just waiting for the next job. These are the active qubits which do the gates in the processing. You can do laser gates here. Sometimes in the gates are also some non-active ions. Yeah, because there are always 5 ions in this game now in the gate region. And now you try to move the ions according to the algorithm, which I showed you before, such that they are optimally shuttled. So that is how it works, see? So you see the number of cost is going down. The thing is optimized. It's sorting itself nicely. And then you have much less shuttles, okay? And it's just a heuristic which scales nicely. So that is now the outcome. That is now what you have to execute. But if you look to before, it was way more shuttle, way more crossings. So that is a really big asset of our architecture, where you can shuttle the qubits and connect them differently according to the algorithm. In a solid state device, everything is solid, okay? You cannot shuttle the qubits, they are just built in. Here you can shuttle them. And you can really play on this and it helps. Okay, so that's after and before. And here is now how it looks then in the circuit. You see now the ones which are close, they are interconnected, they can be really rapidly processed. Then you have some step of shuttling. Then you can rapidly process, then you have some step of shuttling. Exactly as I showed you. So it is a very realistic compiler setting now for our shuttling compiler. Yeah? And the cost reduction is enormous, enormous. And we are in future, that was one question, now we have to pass the ions always along each other. But we can, when we have X junction and bigger structure, we can go to adapt this for a 2D architecture with all the junctions. Okay. Now comes the problem of the quantum errors. The quantum errors are the most awful errors you can think of, because the quantum computer is in that sense an analog device. You have alpha 0 plus beta 1 and assume there is a little error of this alpha and beta. This is complex number with 10 digits and just the last digit is a little bit wrong. can almost not see that this is wrong. Yeah? How can you detect this? A classical error is easy, either 0 or 1. It's easy. You can immediately see it. But these little tiny errors, and the problem is they are accumulating. So if you have a little error here, after a while, it's completely wrong. So see this error, which I now do, you almost, you can see, I did a large error, but a 10 to the minus 5 error would definitely not see. So that is a problem. You entangle this now with an ancilla, and that was the big invention by Peter Shor, actually. More important, I think, as compared to the quantum factoring algorithm, he found the quantum error correction also. So now you entangle this qubit with an ancilla qubit. And you produce an entanglement in the sense that if there is the state with no error, the ancilla has no error, and it is in the superposition with a full error, and the ancilla has a full error. And so far, the ancilla is not measured. That means the ancilla is in a superposition of error and not error, and the qubit is in this little error. Okay? And now you measure the ancilla. Boom. And you have either green light, and then you can forget about this part of the wave function. You projected the qubit to have no error. Or you have a full error, like this, then you know exactly what you have to do. So this is the measurement of the ancilla makes the analog error of the qubit digital, and then in this way also correctable. And the little error means that this happens in very, very few cases, and that mostly does this. But now this scheme is way too simple. It doesn't work. And the reason is that qubit would be measured in this way also. And we would destroy the superposition information also. So that is just to make you clear how from an analog error we go by measurement of the ancilla into a digital error. And then being correctable to start with. But then you have to be more clever. And this more clever is a topological quantum error correction. Now you need more qubits, physical qubits for one logic qubit. Here in this, that's our preference here. 7 physical qubits for one logic qubits. And please don't be confused. This is how theoreticians like to draw it with these plaquettes. These ions are still in a linear arrangement. Yeah, they are still in a linear ion crystal. They are not sitting like this fancy way. But I want to show you here on this fancy way how you measure the errors. Because you are not allowed to ask the qubit, are you up or down? You're allowed to ask qubits, are you alike or not? What is your parity, for example? And that's what you do. You measure the stabilizer states. You measure whether all qubits are in this stabilizer, say X stabilizer, Z stabilizer, whether they have the same spin orientation, whether Z1, Z2, Z3, Z4 is +1 or -1. 1. Plus or -1 is the outcome of this one. And if it is +1, then you know everything is fine in this red plaquette. No error there. And now you measure the blue plaquette, the same thing. And if you find an error, well, you know something is wrong, but these guys cannot be wrong because they belong to the red plaquette. So only this or this can be wrong, and you can check it by measuring the stabilizer on the green plaquette also. And if you find a stabilizer which is 1, then this green plaquette is okay, and this was the bad guy, and you know exactly what to do without asking this bad guy immediately. And that means you can protect the states by doing this quantum error correction. So you have to do these plaquette operations. You have to measure the stabilizers. These are 4 qubits which you want to measure in parity. Yeah? And that's what we are doing. That's the plaquette readout for one of these plaquettes, say only the red one. Here are the data qubits, and you measure them here, and you measure the control Zs here, or the ZZ gates here, one after the other, and then you measure the outcome on the syndrome. Now this is the way how it should work. But then people found out, wow, this is too dangerous, because imagine the syndrome has a problem, then you are correcting the wrong thing, and then you are even making more errors that you had before. So you better have a security belt, that's a flag. And that makes this whole scheme fault tolerant. That's why it is fault tolerant syndrome readout with this additional flag. Then you can also check the flag. If the flag shows red light, don't believe the syndrome. If the flag says okay, believe the syndrome, in short. And that's what we did. 6 eins, 2 of them syndrome and flag, 4 of them data. These are the 6 eins, blue, red, light red, green, dark green, purple. Okay, all these eins. This is the time, that's the shuttling. At that time, we had no shuttling compiler. We had to do it by hand, actually. So that was the optimization of Janine Hilder. Took her a week. If you run it now, pew, there's the shuttling algorithm. So, but it is a lot of shuttling steps. There are 90 configurations which you go through. 90, okay? Transports, single ein transports, 2 ein rotations, that means to change the order. Merging, separating, 21. And the gates, of course. So that's a really challenging algorithm, and that's the outcome. So now we measure the parity of a plaquette, and you see here, 0, 0, 0 is fine. Great, it has a 1. This one is a wrong state. Somehow you imprint the states. So don't wait for the error, but you put wrong data in somehow, okay, and measure then whether the thing works. And you see, okay, if there's 1 qubit here or there, but if there are 2, that's fine again, okay? So it's measuring always the parity of the state. Here is 2, okay, that's great. That's also great. This is a bad one because it's 3 ones or 1 1 is also bad. So you see the single shot fidelity is 92% of the whole algorithm. Of course, to say it frankly, our error correction would completely fail because by doing this, we would add more errors as compared to the situation where you just keep the qubits alone. But if you then post-select on the number of flag raised, that means don't believe the syndrome, then we could boost this 92.3% to 93.2. That sounds like a mix in my numbers, but instead it is an improvement by 4.5 sigma, okay? So it makes a big difference. It makes this fault tolerant. Of course, our gate fidelities are not good enough to really take benefit from this error correction. Not at all, okay? People are fighting, and there are several papers. Some of them I should update this year's appeared. But still, the threshold of being fault tolerant in the operation, this is from 22, this data, is still very hard, very, very hard. So the fault tolerant qubit is not really existing. It's a lot of work, and it doesn't help at the moment too much, okay? So, but that is, at least the algorithm is working. And here you see again, we could inject an error on the syndrome. That's exactly what you don't want to have. That's why you have the flag. If the syndrome has got an error, this error will kick back as a hook error into the data. And then you can eventually generate even 2 errors there, which is then no longer protected with this code. So these hook errors are very dangerous, and we could see that we could insert errors and detect them. Here, see the flag. With a flag, we could detect them with a flag, and we could then, in this way, also detect errors which would not see, but they would be harmful because they are appearing in the face, okay? So it's really cool. You can play with these quantum error correction codes pretty nicely around and test it. And that is, again, the thing I showed you. That is the gate sequence, and you see it is 90% is laser, is register reconfiguration. That means all this shuttling, and only this little part here is the gate part. So that makes it, of course, awfully slow, and that's why we are going to be faster. And that's the next thing. We have one logic qubit here sitting, another logic qubit here sitting, and then we have qubits which are surgery eins, which are commuted between the 2 logic qubits. And in this way, by the shuttling, you can knit together 2 logic qubits in an error-free way and generate larger entangled states, like a Bell state of 2 logic qubits, and then teleport with this Bell state. So you need a lot of eins for this, control all this. So that is on quantum error correction. Now, I think, well, I have a little bit of time still left. It's really long, wow. I've never given really never in my life, and I'm old guy, never given a long talk like this. Is that still okay or? Okay. Okay. Good. Now so one application is quantum error correction I showed you. Now we come to some other application cases. So yeah, here are just sketchy, okay? As I told you, we have, and this is in collaboration with some people, okay? Because that makes it for me also nice. I'm building a quantum computer, and I was an atomic physicist and spectroscopy guy by education and by training and so on, and then I entered quantum computing, and then I had to learn a lot of informatics also on top of it and how to deal with these things. But now it is coming to the moment when you can say, okay, this quantum computer is maybe at some moment at the onset of some nice applications. And not this one, but the next one we built, okay? And and then you are trying to look into different aspects. Where could be the possible application cases of a quantum computer of 50 qubits? And there are not so many, actually. We need much more good algorithms. Many, many more. We have not too many. I told you about the variational quantum eigensolver. That is together with the company Covestro. So the whole idea is you have a molecule. To understand the binding and the reactions in a molecule, you have to understand how the electrons are put on the orbitals. And this is very hard for chemistry calculations to calculate this, because this is a Fermi problem. And you have many electrons and many orbitals, and they have to, they cut the problem typically. They say, if I have a benzol ring and another benzol ring and another benzol ring, this electron, wow, this is so far away from this one, just should not be connected. I can just say this is an electron, this is another electron. But we know these electrons are fairly delocalized. The second thing is, if you are ending with some polymer stuff, you have many, many different levels which are almost equidistant in energy, or almost at the same energy, at the same energy, very little variations of energy. And they make a big change in the chemical reaction. And you cannot take infinite levels around the Fermi level. You can just say, okay, I take the first 10 electrons occupation here, and then I say, okay, there's nothing occupied beyond and everything occupied below. And here's my Fermi level. I calculate this ones, and then I'm sure they are fully occupied. They are never occupied. But that's wrong, okay? And so there are really challenging problems. And the idea is now to convert this chemical problem into an Hamiltonian, to optimize the Hamiltonian in terms of energy, and that is variational. So you creep down into the valley of this energy. That's the variational quantum eigensolver for chemistry. And for a multi-flavor Schwinger model, which I had no idea about, okay? I had no idea about chemistry, I had no idea about multi-flavor Schwinger. So this allows me now as a physicist to learn new stuff. That's really nice. You know, you can beyond quantum computing, you learn now the application cases. I like it very much. And error correction is one I showed you, but there's also the quantum autoencoder, a very cool thing that connects quantum computing to machine learning. Because typically you say, okay, here's my algorithm. I have a friend who is a theoretician, he knows the algorithm is like this. I implement this. But this is a different approach. We say we take an ansatz and then let the quantum computer learn the good algorithm himself, okay? He should just do it and do it and do it and learn it. And we just tell this is wrong, this is wrong, this is good. And this is good, that's better, that's not better, that's not better, that's better. And then after a while learns really the right gate sequence. So that is something I want to show you now. That is the quantum autoencoder, work together with Markus Müller. And the idea is we want to learn how to protect 3 qubits against a qubit flip error. Well, this is what Peter Shaw told us. So we will not learn too much new, but we want to start as innocent and no understanding of the system and just having initialization of the qubits. So here are a state coming in. This is 0, alpha 0 plus beta 1. And we give it another 2 qubits because we know you need redundancy. And then the quantum computer itself should find the right algorithm to protect this alpha 0 plus beta 1. Okay? And we are doing nothing on the gates. Yeah? We just let it do. We initialize this. Then we have a very complete ansatz that is characterized by some gates here and some parameters of these gates. And then these qubits are not used, okay? And then you're just checking out whether this qubit is okay. And you just reflect this answer to the quantum computer and let the quantum computer, of course, you measure this one, and then you say, okay, sorry, it's wrong. Yes, it's good. No, it's wrong. And then let the quantum computer develop the search for these parameters. That's how it works. So, yeah, you initialize in 0, 1, or you take different states on the Bloch sphere and transmit it through the circuit. And the answer, that's the initialization. You make redundancy. You make a belt state, then you make a GHZ state out of it and say, okay, with this guy, enter into the ansatz. And then the ansatz is a pretty, that's the initialization, and then comes the ansatz. And the initialization should protect against an error, okay? So we make an error. Here we make an X error, X error, X error, or no error. So we make an error, okay? And then we say, okay, now it's your problem. Quantum computer, do your best. And the parameterized ansatz is looking like this, okay? That is the ansatz. You see all these parameters here. Nobody knows what theta 8 is, theta 10. Well, try it. 16 parameters have to be trained. And all these gates which you have to do this. And that's what comes out of the simulation. That's first the simulation. So there are different classical optimizer. We use this SPSA. And there's this, where the quality of the thing increases when you train it longer and longer. These are always 200 count cycles. That means you do 200 repetitions. And then you have 200 times 100. That, you know, every time you update the new parameter after 200 count cycles. And then you can find all these parameters. These are the parameters, by the way, here. And some of them look like pi, okay? Not exactly pi, but maybe pi. I don't know. Or pi over 2. Maybe this is a pi over 2. I don't know. It's just numbers. And then you can run it on the computer. That's now on our hardware. That's now red trap, okay? That's our eins, which do the job. And they do the job pretty nice, you see? There's a little errors here, yes. But it's pretty cool. It learned its own ansatz, and it does the whole job, huh? Without knowing. So Peter Shaw's paper is kind of reproduced here by auto-learning. And that's how the parameters are evolving. You can now learn how the quantum training would be done, okay? You start and then look what the parameters do when you are evolving. And the cool thing on this is that you are, with this scheme, you cannot learn too much. But if you taking 5 qubits, you can learn the errors that the quantum computer itself does. So you learn the errors which you don't know. So the quantum computer learns its own errors and can optimize against, it can learn the native errors of this very quantum computer. So it learns its own errors and compensates against its own errors. That's something I really like, because that will do the really good error correction for this specific device. Yeah? Okay, then we had a little bit of chemistry. I'm joking, H2 molecule. You need not too many orbitals. That is a very easy algorithm. But still, actually, it's not about the algorithm. We can do much more complicated algorithm. But I think the workflow was cool because you start with a chemical problem. You make out of this a Hamiltonian. We are Wigner-Jordan transformations. You make out of this a circuit. You run this through the optimizer, through the shuttling calculator, compiler. Then you run it in the computer. You have the connectivity to the optimizer. The classic computer optimizes the results. And then you see this, okay? And you can optimize for the ground state. And you see it works. Here, it starts with a bad energy and then it goes down and it goes down. And here it is. It settles to this. It's, of course, everybody knows how hydrogen looks like, yeah? That's clear. But it's cool, it works. It's just the whole workflow is there. It means our software is working in the way we want to have it. It's running on the hardware. Okay, and that's how the parameters settle to some. Now you can learn what orbitals are occupied somehow, okay, in the chemical language. Okay, we come now to the last example, which is not yet, I can only show you the intermediate result, because this multi-flavor Schwinger model, you know there are 3 quarks, and they have spin up and spin down, so we need 6 qubits, okay? And 6 qubit is at the level of where we can handle the system barely, okay, to be honest, in our old red trap, because that's the old hardware. And so that is now Carl Jansen, he's a high energy guy. He knows exactly why this is the right model. I have no idea, and please don't ask me, okay? This is a high energy Lagrange density, whatever. And it has some parameters which are the masses of these quarks and whatever, okay, interactions. And we make a simulation of 3 quark masses. And each quark can be spin up, spin down as a fermion, and they have some different phases, okay? And that's what we are looking. That's the minimal model, has 6 qubits. And this is the Hamiltonian, okay? Now it is easier for me to understand. This is much easier for me than this one. Because here I see, okay, I need this interaction, I need this gate, okay? And then I have to measure this, okay? That is the energy cost function, which I try then to minimize for certain parameters, like the mass of this quark or this coupling or whatever, okay? And then I have these parameters, K1 and M1 and so on, and then you can tell, okay, that is what the outcome would be. Now, this is the algorithm if you now convert it into quantum circuit. As I told you, these are the 6 qubits playing the role of these 6 quark states with spin up and masses and so on. And this is the algorithm. So you are, yeah, it is really pretty challenging because it doesn't end here. It goes on, it's very long. It has a lot of ZZ gates and yeah, here are all these numbers. You see, this is now for a specific type of mass and interaction and so on. And of course, these are free parameters which are later on optimized for different settings. And we did it only on a little sub-circuit, not complete, but just for 4 qubits, so it was not the quarks, obviously, but we run this circuit, and that looks really awful. Simulation and measurement is not okay. And that is because we had 1 qubit sitting at the side for quite a while. So I don't know whether you can see this from the algorithm, but you have first to do this one, and then you have to do this one, and then these qubits are waiting, and then you have to do this one, and then only you can do this one. So these qubits are waiting for a long time at the side. And the problem is at the side, the magnetic field is a little bit higher as compared to the center. We're talking about Hertz shifts, but Hertz shifts after a while change the phases, yes? And so this is really need the magnetic map of our trap at a level of Hertz or sub-Hertz, yeah? And that's what we measure. And then we measure this map. That's the frequency, the map here, how it changes over the time, over the space. So there are all these qubits sitting at different positions, and if some qubit is sitting far away here, then gets a stronger magnetic field, and that's what I said. They are not man-made, but we can still spoil them. They're made by God, but we have our inhomogeneous magnetic field. And once we did it, we got this one. So that is now looking much nicer, actually. So now we have this heavy peaks are nicely overlapped from the simulation on our hardware simulation. So that is the status, and I hope that we can get it still done on the old hardware, but that will be really the most we can squeeze out of this old trap, and then we have to go into the new architecture I told you. So that's now my plan. Scale up to 50 and eventually 100 qubits with this architecture that joins the shuttling and the addressing. That means two different architectures in one setup. That is the way it goes. And then we can still have these connected 1D architectures. And the other thing is we need to be really able to establish this 24/7 operation that everybody can operate it at any time. The variation quantum eigensolver, I think, is the most, let me say it differently. A friend of my chemistry person, he says, if you could give me 50 good qubits, I could learn something. And that's a promise. And the option is to do it in the variation quantum eigensolver for chemistry simulation. And then, of course, the quantum error correction we have to push, but I don't give you a clear perspective when the quantum error correction is coming into existence in a real quantum computer. Maybe in a way that we have some of these qubits you have seen in the algorithm. One qubit is waiting so long. It would be good to have this one error corrected. The other ones are used and then discarded again. They are quickly used and going, coming, going. That's easy. But if you have some qubit which are really important, sitting there all the time and keeping the phase and so on, then you should do something. So partially error corrected, maybe I could promise in 5 years, but fully error corrected, it takes so many overhead in terms of qubits that I really would love if we have within the NISC noisy intermediate scale era with our physical qubits that are tuned to be so good as possible that we have still some application cases which are meaningful. And then, of course, comes the beyond 100 in 2D architectures. I showed you how we go the baby steps. And in future, I think every computation center should have a quantum coprocessor attached to it. So that's the group, and I thank you very much. I'm ready for your question. I'm coming way back. So how much back?
Okay, wait, so that's
Further back.
further back. The
Further back.
Zologate.
Ah,
Yeah.
okay.
But maybe I can just ask you, and
Yep.
the slide is not important, but
Okay.
if I understand correctly, you need to be able to address ions individually for the.
Yes.
Is that not the case even in the spin-dependent?
No, for a single bit operation, you need to address one ion individually.
For
You should have no crosstalk to the neighbor. So if you want to do a pi pulse on this ion, the other ion should not see anything from this light.
and this is only for single qubit gates.
A
Not
single qubit gate should only work on this very single qubit where you want to do it. If you have spillover light to the other ions or do something harmful to them, it's very, very bad. So these crosstalk errors are not nice. Yeah, you have to really but that is possible. If you are taking just a Gaussian beam of 2 micron, the overlap to the next ion, which is 4 micron away, is super small. And if you actually have additional tricks, also with spin echo techniques, to get the parasitic rotation of these other ions spin echoed away. you can think of this like doing a composite pulse by not doing one pi pulse, but doing it in 2 steps and changing the phases, but not for these other ones. And then for the other ones, it's compensated, and for this one, it's adding on. So that is a trick that you can play, because it's a coherent interaction, and then you can do the spin echo thing. So, but you should not have any crosstalk, actually, yes. Yeah.
Even far back, like when we were talking about the regions of stability for the ion trap, like when we were talking about the pseudopotential and how we approximated that to a sign, but like it was like a sign with like a couple of wiggles on like the tops and the values. Are there like any measurable physical effects associated to like, you know, those little wiggles at the value or at the top?
Well, the wiggles are always at the top, because the electric field is 0 at the center line, and the oscillation and the electric field strength increases quadratically. That is this potential which we form. Okay, we want to have a quadratic we want to have a linear restoring force. That means the quadratic potential. And at the center, the quadratic potential is 0. So if you are close to the center, these wiggles are not existing. The wiggles are only existing if you are shifted out of the center. And this shift out of the center is either, that would be the primitive way, you have some charges, some charging of the trap. Say you have a piece of dust, and that this dust is a little bit charged, that pulls the ion a little bit out of the center. This would be a bad thing. Then you have to compensate for this and shift it back into the center. And then you see the wiggling disappears. The wiggling only appears if you're off center. So the ion wave packet really is well placed in the center. It has a, so getting orders from magnet is about 10 nanometer large, the ion wave packet. It's a Gaussian wave packet. And the you are typically much better than 10 nanometer in the center. And if you are not, you can sense it. If you are shifted systematically off, you sense it and move it back. The problem is just if these things change over the time, and you are first working without, and then after half a day it's charged up, and then you are degrading your performance in this way. So that is awful. That's why you need so nice gold covered surfaces without any dielectrics on top or insulators. Yes. So that is certainly a problem if you're dealing with bad traps. Yeah. Then it's changing over time, this micromotion. But you can compensate it very, very nicely. And then it's no problem, this wiggling, because it only appears if you're off the center, because there you have electric field strength. And that, of course, changes polarity, because you switch from minus to plus, back and forth. Yeah? But in the middle, 0. 0 is always 0, regardless minus or plus 0. Okay? Yeah. Yeah.
Hi. So from what I understood from reading some literature,
Yeah.
with this shuttling architecture, I had the impression that one big drawback for this trapped ion quantum computing is the cooling, because, for example, with the 2 qubit gates, when you use these vibrational modes, that the majority of the time is spent on cooling down each individual.
Yeah. Well, the cooling is certainly necessary. Well, optical cooling is reaching temperatures which you can never have in a dilution fridge. Actually, this even Doppler cooling, and that is something silly for us. So Doppler cooling is 50 times colder than a dilution fridge typically, and sideband cooling is even much more deep down. So you are comparing a little bit apple and pies, I would say, but the cooling is always a problem. But the problem is really solved by the different gate. Okay, the gate which I showed you, that's this the ZZ gate, not the Dirac-Zoller gate. The Dirac-Zoller gate is not immune against phonon excitation, but the Møllmer-Sørensen or the dark shift gate, where you employ this AC Stark shift, which is different on the spin states. That makes a phase trajectory, and as I told you, this phase trajectory comes back to the origin regardless if there's one phonon in or zero phonon. Of course, it is not perfect. Everything is not perfect. If you have 100 phonons in, it doesn't make a different circle, and then it is not good. So you still need cooling, yes, 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 but it is much relaxed. And then you are addressing all these many, many modes. I showed you the EIT cooling for this, I think, 18 modes of the axial motion. And that has this advantage of cooling all the modes in one go. Because if you are, you see, the Doppler cooling has a very broad resonance. It cools all the vibration modes, regardless on their frequency. It cools an oscillation of 1 megahertz, but also equally well an oscillation of 5 megahertz. If you do resolved sideband cooling, you can only cool one mode at a time. And then you are totally right. If you have 10 modes, you have to cool this mode, and this mode, and this mode, and this mode, and this, and this, and this, and this, and you're never ending. So that is the problem of resolved sideband cooling, where you are the other. Now, the advantage of the EIT cooling is that you are tailoring the line width of the cooling by the quantum interference to cover a band of vibrational modes which you want to cool. So you cool all of them simultaneously, not perfectly to the ground state, but almost to the ground state. That's the little price you have to pay. The sideband cooling is still colder, but you cool them very cold, actually, I showed you. And that is sufficient for the gate, especially for the hot gate. Yeah? So the cooling problem, we have some cure, I would say. Yeah. Yeah. Okay. I cannot throw it over. I feel worried.
So in ion-trapped quantum computers, you have this problem that for large-scale systems, those transcendental waves start appearing at the end of the ion-trap. I was wondering, transversal modes start appearing.
Yeah.
I was wondering if shuttling can help with this problem.
Yeah, of course shuttling helps because you cut the problem into much more, yeah, absolutely. No, completely, all these mode structures are becoming more complex and less easy to handle if you have large ion crystals. So pieces of, I tell you frankly, a 10 ion crystal I'm not at all worried about. So if we cut down the thing into pieces of 10 ion each, no problem. If you handle 100 ions, it's exactly what you say. There are all these kind of modes, cross-couplings, and so on. Many, many different things appear for the large systems, but that's why I should obey the Roman emperor rules, divide et impera. Huh? Yeah, I think that's still good. But not too small pieces, because then you have to handle everything. Then you are ending the other optimization problem. Yeah, yeah, no. 10 ion crystals have not this problem. So crystals of a certain length, they become then problematic. And then you are, as I said, you are fighting many, many problems. Actually, the recoil problem, the mode narrowing, that they have many narrow, the gaps are becoming smaller and smaller between the modes. Frequency-wise, you have a problem. Recoil-wise, you have a problem. You have the zigzag transition appearing. You have, well, name it. All these kind of things happen. And the addressing is also harder because, well, in a longer ion crystal, as you see in the middle, the ions come closer and closer. Yeah? If you have a very long ion crystal, the ion distances at the middle become like 2 micrometer, and then it's hard to address one and not touch the other one. So that is why we are staying with a conservative 10 ion crystal approach, where all these things are not happening. And you can still handle it. Yeah. Yeah.
Actually, I had a follow-up question based on his question due to the wiggly nature of the ions.
Yeah.
Say, I would only presume that this problem would grow if we go on to build a 2D mod to the architecture of the ion trap.
Mhm.
How do you plan to counter?
Well, there is, yeah. I should go to this one actually. To this one. That is exactly the problem. So we perfectly well know how to handle the micromotion in this part of the quantum computer. There we do it. But here at this Y junction, you have uncontrolled micromotion. So this is now a dangerous moment to go through. Here, the ions will undergo some micromotion. Why? Why? Think you are coming as an ion, and you have this radial confinement. Now, at the moment you see this other electrode, which is wiggling in this direction, okay? The wrong direction. It's no longer this. Normally, this is a confinement X and Y, okay, here. And here it is converted into this confinement. So you are hitting a wall. That's the micromotion bump, which we know. That's this thing which happens here. And you can optimize the geometry, and that's why we need these bars here. So it's really a great question, thank you. So we need these bars to get confinement. If you are connecting two quadrupoles, or actually 4, 1, 2, 3, 4 quadrupoles, you cannot match the fields such that there is a quadrupole at the center. It's just not possible, okay? That is a higher order multipole in the middle with no quadrupole at the center. So there is, in the very center, this is not a nice trap here, not a nice Paul trap. It's confining, but in a fancy way. And you have to go through this to this junction. Well, you will make it somehow. That's my personal way how I would handle it. I will handle it like this. If you are doing the transport of an Y or X junction, you certainly need to cool it down again. You need some good cooling afterwards. You cannot shuttle it through this junction without some harm on the motion, I think. That is because of this non-quadrupolar field in the very center of these things. Yeah. But then you have to do recooling. Yes, that takes maybe a millisecond. Yes, that delays the quantum computer. Yes. Yeah.
I think we're going to finish. So, thanks a lot. Thanks again. And
Thank you very much.
I mean, for the first time, you give us a long list.